Where is the power?
Is that cable that comes down?
No.
Okay.
Oh. But you need to actually straighten the thing. So. Yeah, I need to do
The memory part isn't the actual memory part. Should I No. Some are not. A reminder. Actually, a lot of people got run out. Okay, hi everyone. We're going to start in a second. Sorry, we're running a little bit late this morning. But while we're waiting for the folks who are here, I just wanted to ask if people, as of now, there are 28 people who've gotten their $100 from the cluster time. So 28 is a lot less than the total number of people we have here. So I was curious if people are either running into any problems setting it up, or just haven't gotten to it yet, or don't intend to. So that's, I guess, 3 options, right? So 4 options if you've already done it. So who here has already set up their account and has the money, or has requested the money? Okay. Who is planning to do it, just hasn't gotten to it yet? Okay. Who is running into any problems with it? Okay. And who doesn't, I guess you won't raise your hand. Does anyone not intend to do it? Doesn't want $100? Okay. So does everyone has the instructions though, right? Everyone has gotten the instructions. If you haven't, come talk with us. It should be, well, I'll give you a second. But it should be hopefully fairly easy. It's intended to be easy, so it's $100 each. Hopefully that's appealing to everyone. So if you are having any trouble setting it up, just let us know. Send us an email. The instructions are on the Google group. Hopefully it's self-explanatory, but yeah, let us know if there's an issue. Yeah, that's good right there. Alright, so let's take care of first.
Okay, so good morning, everybody. I'm Deepak. No, I'm obviously not. So we're not quite sure yet where Deepak is at the moment. We'll find out eventually.
9:30, he says.
9:30. Okay, so I have half an hour to tell you all sorts of things that, well, I have to figure out exactly which slide to pick, right? So apologies for that. So if you bear with me for about 5 minutes to find a slide set that's actually suitable, and that, well, basically Keynote has not managed to mangle yet, so because the latest Keynote version is not. Don't record this yet, please don't. Just bear with me for a moment. And
He's still streaming live there, right?
yeah, I know. That's embarrassing enough. So what I'll do is I'll talk a little bit about hierarchical models, and if at some point the slides are messed up, then thank Apple for that. They've gotten better at mangling their own file formats than Microsoft are. Never thought this would happen one day. Something later on. Okay. So we can probably start. So, in contrast to last week's lectures that were probably a little bit on the more relaxed side, those slides are going to be a little bit on the more technical side, at least. So there'll be equations. So basically, what I'm going to talk about for as long as the time it takes for Deepak to show up is a little bit about hierarchy and structure in modeling, well, basically data. And because this is actually, I think, a really important issue. So first, I should probably say thanks to some of the people involved, and I've tried to pick the most favorable photos of them, right? So let's actually start with something very gentle. So there shall be slides eventually, equations eventually. But let's start with something very simple. So the simple thing that we're going to start out with is clustering, right? And so what I can do is I can cluster dogs and cute cats and dinosaurs, right? And if I were to do that, then something called the Dirichlet process, which is basically a model of having variable numbers of clusters, and essentially inferring the number of clusters at the same time as you infer, well, the cluster IDs themselves, is a pretty good strategy. So without going into all the math that goes with it, because that would take more than just 5 minutes, you can think of the mechanistic interpretation of this, which is sometimes also when people talk about the Chinese restaurant process in this context. Who has heard about the Chinese restaurant process before yet? Oh wow, that's pretty good. Okay, so if you haven't heard about it yet, here's how it goes. Imagine a Chinese restaurant with an infinite number of tables. Okay, so similar to Hilbert's Hotel, Chinese restaurants. First customer walks into the restaurant. Okay, well, sits down at the table, and well, eats something. And then next customer walks in, and he sees where people are sitting. In this case, there's just one customer there, right? And now, with probability proportional to the number of people that sit at this table, he joins the table, because people are social animals. And with a constant fraction, well, with a suitably normalized constant, he picks a new table. Let's say this constant equals 2. Then, well, if there's only one person sitting at one table, then he picks with probability 1 over 1 plus 2, so 1/3, the table that's already got one person sitting there, and with probability 2/3, he picks a new table. Now the third customer comes in, and with probability now 2 over 1 plus 1 plus 2, right? He picks, with probability 1/2, he picks a new table, and with probabilities 1/4 each, he picks one of the two existing tables. Okay, so what you can see is that this very clearly gives you a distribution over partitionings of, in this case, well, customers to tables. And I forgot to mention to say that while the restaurant has an infinite number of tables, and the tables can hold an infinite number of people, there's only space for one dish per table. Yeah, okay. It's a mathematical construct. So what you basically get is, through that, is a clustering. So you could imagine a new image comes along, and, well, if it fits, the dinosaurs really well, okay, it goes to the dinosaur table, or the dog table, or the cat table. And if it doesn't really, it generates a new table. Okay. This is the Dirichlet process without math. Now, you could argue that, well, maybe cats and dogs are more similar than cats and dinosaurs. And, well, we can make this a little bit more extreme to really drive home this point. If I have cats and dogs, then I have more specifically German Shepherd, and here are some poodles. And they're cats, and you could argue that these are really close, right? But, okay, and they're cameras. Then it probably doesn't make sense to have a flat clustering, right? And that's exactly what Adams, Garamani, and Jordan did, right? So they said, well, maybe we can cluster cats and dogs, but then, maybe dinosaurs are one level higher up, and cameras are a different beast yet again. And yeah, basically, well, two different types of dogs are really something that belongs to the dog cluster. Now, this is a hierarchical modeling where you basically have a hierarchical structure that is imposed upon, the sets of objects that you have in your collection. The reason why I'm going through this in a bit of detail is because people typically confuse, and this is me included, various notions of hierarchical modeling. So you can have hierarchy in your data structure. You can also have hierarchy in the sense that, well, first one thing affects the data, then the other thing affects the data, and you have hierarchy this way. You can have a lot of other more sophisticated structures in your data. The point is, you need to actually specify what you mean by hierarchy before you can say, well, I'm doing hierarchical modeling. Okay. This is one, and the paper by Adams, Garamani, and Jordan, which is a really nice paper, they applied this to images. They made some strange decision about, the hierarchical inheritance between clusters, but basically what they got out as the top-level cluster when clustering all the images. Can somebody guess what that would be? Maybe you would think this is like the God image, right? Okay. Anybody guess? Well, if you've read the paper, this is not okay. That doesn't count. Somebody who hasn't read the paper. Come on, it's Monday morning. Yeah, a cat? Not quite. It's an inanimate object. Okay. A lawnmower. Yeah, exactly. That actually suggests more that the generative process that they used, they made certain design choices to keep the variance at bay, and I think if they changed it a little bit, they could have probably gotten a more meaningful top-level image. There's another thing, and we already talked about that last week, namely factorial representation. So this is latent-to-display allocation, and there you don't assume that each object just belongs to one category, but it's composed of a sparse mixture, preferably sparse, of a couple of components. So think of the traffic light. The traffic light's either red, green, or yellow, and that's about it. Whereas the pixel on your computer screen is a mixture between red, green, and blue. So in both cases, we have three colors to describe the state. However, in one case, we have a mixture between the states. In the other case, we have only one of the three. And that gives very different color representations. Unless I was to switch the traffic light so quickly that your eye would blur everything. But yeah, we're not worrying about that here. This, by the way, is an idea that people used to use a very, very long time ago when basically high-resolution displays were really expensive. So they would actually have a red, a green, and a blue light flashing at alternating orders very rapidly to fake an RGB display. And these displays were really awful to look at. But so it's not totally unconceivable that you can do this. So the next thing that you can do is you can have what's called a hierarchical Dirichlet process. And then there's also something called a nested Chinese restaurant process. And as you can already see, the nomenclature for those models is confusing at best. So the hierarchical Dirichlet process is one where you basically have a distribution, and then at the next level down in your model that you're trying to describe, you assume that the distribution of the child is related to the distribution of the parent. So here's an example of what you could do. You could have that, well, H, so this is again our Dirichlet process that we saw before. This would be, the model that describes, language. And let's just do something as primitive as bag of words. Now, if I have such a primitive model as bag of words, then G0 is going to be, for instance, the base level language distribution for all English documents. And then what I can do is I can use GI to model regional dialects. And so what you would assume is that G0 encompasses the entire vocabulary that's also prevalent regionally, because this is the whole English language. And you would then assume that GI is drawn by using G0 as a prior, but it could obviously be that certain words occur much more frequently here than somewhere else. So for instance, I would imagine that in the Pittsburgh language model, the words pirates and steelers are much more frequent than, let's say, in the Bay Area. Okay, so this is one way of having hierarchy by essentially inheritance from the parent to the child. So basically what you simply do is you have one reference distribution. Here's just some distribution over tokens, which gives me the base language model. And then I use this base language model as a prior for the GIs. Okay. So you can do that. What you can also do is you can play the same game for topics. This gives you something like the nested Chinese restaurant process. So where basically you apply this now not to the language model itself, but just to the topic distribution. One of the problems with this is quite often you need to actually predefine how these graphs are structured, because otherwise it just gets a little bit messy. So let me just write out exactly what happens in the nested Chinese restaurant process. So for each node in this possibly infinite tree, you go and draw a topic independently. And then for each document, you go and draw a path over the tree, and then basically use this as a way of getting the word distribution and so on. So in other words, well, we have our topics here. Then if we have a document there, it actually generates its words by going down the tree. Which is kind of nice, and it actually fits documents a lot better than a flat topic model. Because what you can now do is you can have things like, photography as one level up, and then further down in the bottom you can have all the various differentiations about photography, which is neat. Okay. The problem with this approach is that quite often, well, you have actually variable degrees of resolution in interests, in content, and so on. So if you think about what you're really interested in, there's a whole bunch of things that you're very, very, very specifically interested in. So maybe within, computer science, you're interested in machine learning. At least I hope so. Otherwise, it wouldn't be here. And then within machine learning, you're interested, for instance, in non-parametric Bayes. And then, by the way, within non-parametric Bayes, you particularly like the Indian buffet process, right? This is a very, very specific narrowing down of interests. But maybe, besides being very specifically interested in the Indian buffet process, maybe you also kind of have a passing interest in kernel methods. And besides that, maybe you like classical music, and then you like a very specific painter. And then maybe you speak English, right? So what I've just described is different levels of detail of interest, different types of interest. And if you think about yourself, you may have different degrees of depth and breadth for different interest types. And the models that I described so far don't capture this. So there are some models which are pretty good at essentially just covering, the breadth. There are some models that are pretty good at covering the depth, but none of them actually captures both. And I'm kind of sort of already leading you towards what you would want to do if you want to capture depth and breadth at the same time. And I'll show you, how the math works on the next slide. This doesn't only happen with users. You might also have that with documents. You might have an article about some very specific event, like, for instance, yesterday's Soccer World Cup, right? So then you have, very specific details about very specific soccer players. And then you have, well, by the way, the World Cup, and then maybe it's about Brazil, and then maybe you have a couple of words about, how life in Germany and Argentina is respective, right? And then maybe because it's on the CNN website, you have 3 lines underneath, plugging some other program. So that would be a typical article. So what we therefore want is we basically want to have a tree distribution per object. And this tree, with various levels of depth and breadth, will then cover the content. So what I'm basically going to do is I'm going to attach weights to the possible internal nodes of the tree, and that set of weights should represent what's going on. So let's have a look at this in a bit more detail. So basically what I do is I take a generative process that models a global interest distribution of what people are interested in. So let's say here is Schweinsteiger, here's Messi, here is, well, Klose and whatever, and then maybe, here's the Tor, and, well, it just goes on like so, right? So, yeah, and this is, one gigantic object. So this is in all details, all the things that people are. Now, for each document, and for each word, what you do is you basically select a path within a document. So this is a proper subtree of this tree. This one here. And then, if within that path of the document, if I decide to add a new topic, so this is the same thing as opening a new table in the Chinese restaurant process that we saw before. Then you go and see, well, do we already have such a topic in the global, language model? Okay, if it's there, it's good. If not, then I also add a new page in the global model and then add a new path. So basically, what happens is I always make sure that the global tree is a proper superset of the local trees. Well, let's have a look at an example. So let's say I sample this path. Well, this path, can somebody find it in the tree? In the global tree? Well, I guess that's really easy, right? That's fine. So I'll start there. Now, if I decide to, well, add a new agent in the local document, okay, well, be it so. Remember, we have this. So now that local tree grows, but it's still a proper subtree of the global tree, so no big deal. However, if I go and add a new, topic that's locally new and also globally new, then I also need to augment the global tree. So all you have to do now is, at least at the global tree, is keep track of the counts of essentially how many times this global tree was invoked. This is a little bit more tricky than just keeping track of the aggregate counts, because you need to basically attribute blame as to where those things came from. But there's a couple of really nice, essentially tree samplers which do this. But this is the conceptual structure of having hierarchy, variable depth, and variable breadth. So let's actually see how this behaves in practice. So this is a paper we had 2 years ago. Basically, for each word in a document, you go and sample the node. Then if it's globally new, you, well, add a new node and otherwise. So basically, all we did is for the emissions model, we just used a multinomial. Okay, so here's what you get for the NIPS corpus, for instance. And it's kind of cute because, well, you can see, so overall, well, you get just the fact that it's a NIPS paper, right? Model, system control, policy-based paper, approach, results, data. Any self-respecting NIPS paper has to have that. At least this was 10 years ago. I mean, by now, probably deep would be also a word up, right? And then, well, remember these were the times when parallel methods were actually quite popular. Distribution parameters, basic vector data, and then it would, well, this is actually going for its own parametric. So then you have the algorithm inference sampling and approximate inference, and then you have the more stochastic process papers. Can somebody get Deepak, please? He doesn't find the engine. Okay. So, and then for reinforcement learning, you have the multi-agent, and then you have the, well, more state distribution type of papers. So, what you basically got is you can now clearly see that you have various levels of detail, and you also have various levels of resolution. Well, the entire thing also fits the data really well, and here you can see. So while I'll just continue talking until Deepak is done setting up, but let me just introduce Deepak. He's director of all things machine learning and recommendation at LinkedIn, and I think probably the driving force behind essentially all adaptive estimation at LinkedIn. So it's a great pleasure to have Deepak Agrawal here. Let's give it a And for location modeling, you simply have to read the paper. Can you stop the video? Thanks.
Mirroring what you no, that was probably not. Sorry, this display is a little bit more temperamental than I thought. Oh, okay, I think I know what's going on. Screen background. So I thought this was the entire display. Yeah, that's okay. Can you do the sound check, please?
Yeah, can you hear me?
Yes.
Because we need to make sure it doesn't concentrate.
Alex, you want to connect the microphone for the room also?
Fun?
You want to connect the microphone for the room?
Oh yeah, that would be a good thing. Yeah. I will do that in a moment. You're going to get a second microphone. Do you have a microphone? Okay, so now, otherwise it's just vibrated.
So thank you. So again, I'm going to talk today about recommender problems for web applications. Most recommender problems are on the web, but there are others.
Okay.
Thank you. And these are my collaborators at LinkedIn. About myself, so normally I don't oversleep. Somehow, I don't know what happened today. I was not able to go to sleep at night, and I went to sleep at 6, putting in an alarm, but I overslept. So that generally doesn't happen. It's the first time it has happened. But yeah, I got my PhD in statistics, in spatial statistics. Then I spent 4 years at AT&T Research, and I was working, as you can imagine, working for models for call graphs, which AT&T had. Who called whom, what can you figure out about the user based on the call graphs, and so on and so forth. Then I was at Yahoo Research for 6 years. In fact, Alex was my cubemate. We used to have a lot of conversations, and I learned a lot from him in the process. I was mainly working on content optimization and computational advertising, which are again two particular applications of recommender problems, as you'll see as we go along the lecture. And finally, I have been at LinkedIn for 2 years, and here I have been more in a management role. So I don't know if it's good or bad. I'll leave you to judge based on what you see today. And there I have a group of machine learning folks who are working on building ML platforms and also working on optimizing all consumer-facing recommender problems like the content recommendation you see on LinkedIn, people recommendation, email recommendation, profile completeness, endorsement, and so on and so forth. Okay. So again, just a disclaimer before we begin. This is the usual stuff. So this is the agenda. I'm going to go through an introduction of recommender systems very quickly because you have another lecture on recommender systems by Javier later on. So I'm not going to spend too much time, but I'm going to give you an introduction which is going to be more germane for the kind of stuff I'm going to talk later. Then I'm going to talk about offline components, and again, you don't need to worry about this now. You will see as we go along. So there are three different things I'm going to talk about as far as recommender systems are concerned. One is how do you build offline models. to initialize what I'm calling the online models, and then we're going to explore, exploit, and banded solutions. I'm going to talk about how you evaluate recommender systems in practice. So if you have a bunch of data, and how do you evaluate a method before you deploy it in the wild, and how do you evaluate a method once you've deployed it in the wild? Right? There are two different things here. I want to talk about doing multi-objective optimizations. Often the goal is not to increase the total number of positive ratings or to increase the total number of revenue or clicks. There are multiple things involved when you're building a recommender system. Right? If you increase the total number of clicks on ads, you might start losing revenue, for instance, because you're getting more clicks, but on less pricey ads. So how do you balance these different competing objectives, if you will? And that kind of comes up in many different recommender problems when you're working with one of, especially when you're working on a commercial one, on many of these websites. And finally, I'm going to end with some challenges. So we're not going to cover all of it today. We have a lecture tomorrow as well. I'm going to try to go through all of offline components and maybe some of online components, and the rest we're going to cover tomorrow. But again, feel free to interrupt me. I want it to be interactive. If you're not following anything, stop me. If I'm going too fast, stop me. If I'm going too slow, yell at me, and I'm going to speed up. Okay, so recommender system. So before we even go into what is a recommender system, the first thing is why do we need such things? Well, the answer is very simple. You need them to improve the relevancy of information which you get over and over again from various different channels in our daily life. I mean, we are all living in a world of information overload, where you have more information available than what you could consume, right? And so getting the right information, the most relevant information in every single context is extremely important. So in the old days when you had newspapers, it was all done by humans, right? I mean, the editor is going to take a look at all the material given assembled, and then he's going to look at the newspaper, he's going to edit what goes where. That worked, but it only works for newspapers. It's not scalable, especially in the web age, right? You need a better mechanism, a more cost-effective mechanism to make it effective. And so that's why we have recommender systems. So roughly speaking, these are computer programs that are used to automatically serve the right item to a user in a given context to optimize some long-term business objectives. Okay? And again, it is a scientific discipline that involves various sub-disciplines. Machine learning and statistical methods are, of course, at the crux, at the heart of all recommender systems you see in practice. Then you need large-scale optimization techniques. So a lot of optimization literature, linear programming, quadratic programming, and so on and so forth. Those are very important. User modeling, that's very important, right? But at the end of the day, if you're reading the mind of a user and figuring out what to serve when, how to model a user's behavioral characteristics, how to model a user's intent in a given context, it's extremely important. And so I've called it out separately from machine learning and statistical methods because this is an extremely important component of the entire recommender systems. And finally, natural language processing, to understand what the content is all about. If you're recommending a news article, you better know what the news is all about. Is it about World Cup soccer, or is it about a political article? What is it about? That helps you in making better recommendations. Right? If you know a user is not interested in software at all, which is hard to imagine, but suppose you have a user who's not interested in soccer, and you're not able to know whether if the article is about soccer, that's going to sound all great to the user. Not a good recommendation. Understanding users and also understanding what the article or the content is about are both very important to make good recommendations. Okay, so here is an example. I'm just giving you some examples of recommender systems. So again, these are the ones I have worked on myself in the past. So I can speak to them more than others, but there are many. So this is the Yahoo front page, and again, this is, as you can see, this snapshot is from the previous work, right? So I don't work at Yahoo anymore, so I didn't feel good to take this screenshot now. So I've taken a screenshot 4 years ago, that's what I'm showing you there. So this was the World Cup recommendation that was done last year, right? So as you can see, the Yahoo front page back then consisted of various sections, right? So you have what we call the Today module, the News module, then you have the Search Query module. These are all the apps module, right? So they used to sort of apps on the right rail, right? Nowadays it's gone, I think. right? And so for each of this module, you have a content inventory from which you can choose from. When the user comes, you have multiple choices, right, on how you're going to fill up the slot. And the goal at the end of the day was to figure out what is the best way to fill up this whole page and the user visits the site to maximize some objective of interest. Now, the Yahoo front page served as a fire hose to funnel traffic into various other parts of Yahoo. So click rate was an important objective here. If you increase the number of clicks which you are having on the first page, that's going to drive more downstream page views to the entire Yahoo ecosystem, right? You're going to get more people visiting Yahoo Sports, you're going to get more people visiting Yahoo Finance, and so on and so forth, right? So it was an important objective. The objectives are not always as straightforward as this one. And even for this one, you'll see later on in the lecture, there is not just one single objective. There are multiple objectives here as well, right? But for the moment, assume that the goal is to really improve the number of clicks you're getting on this page, because you can send more stuff downstream from the Yahoo. Right, so that's an example of a recommender block, right? And, as I said, so this is the problem here. Online advertising. I'm just showing you a cartoon here because there are so many companies doing online advertising. Google, Yahoo, Microsoft. But there are so many ad networks. So online advertising is a very mature market. But here too, it's a recommender problem. Why? Because we have a user coming to the page. And then you have advertisers who have created the ad inventory. Right? So the advertisers, based on some offline marketing studies, target a certain segment, a cohort of users. Right? Like if you are selling some clothes, women clothes, you're not going to target males, right? Although you could, right? Because males can also buy women clothes, right? But yes, that's beside the point, right? So advertisers do offline study and come up with some broad segment definition. And they say, okay, well, my ad should be shown to this particular segment of users. But within those broad segments, there are many different users. There's a lot of variation in what these users would like in terms of ads, right? So a user comes in on a page, you have a bunch of ads that are available to be served, and the recommender has to pick the best ad to be served to that user, right? And the optimization here is not just click rates, it is the expected revenue that accrues to the advertiser. So if you have a lower click rate ad, but the advertiser is willing to pay $20, that might still get shown compared to another ad that has 4 times more click rate, but is only willing to pay $1 per click. However, ad networks also want to make sure that you don't show very low quality ads on their site. So what I just described is not exactly what happens. There are other knobs that are all there. Those are more secret sauces of different ad networks, which they don't reveal. But at a high level, that's the problem. Right? How to serve ads to a given user in a given context to maximize expected revenue to the advertiser while maintaining the quality of ads for the brand. Yeah. Okay. So this is an example from LinkedIn, right? So if you go to LinkedIn's homepage, you will see a news module on the top, right? And again, the same problem as Yahoo front page, except that the content pool here is very different. It's more professional news, more evergreen articles, not too many trending articles. We have opened up our publishing platform for others to write blog posts on. So there are a lot of candidate articles are articles written by ordinary LinkedIn users on the platform itself. Right? So very different kind of content, but nevertheless similar to what I was describing earlier. Then there is advertising on LinkedIn as well. Right? This is people recommendations. So if you go to LinkedIn or Facebook, you will find the system recommending you other people to connect to. And this is extremely important for social networks, right? The more connectivity you have among users in a social network, the more benefit you get out of going to that page, right? Because if I connect to you, and if you change a photo on your LinkedIn profile, then I can show it on your newsfeed, on my newsfeed. Right? So connectivity is important, right? It drives a lot of engagement on the network, right? And so all social networks pay a lot of attention to people recommendation. Okay? So this is an example of people recommendation. These are recommendations for me, and again, these pictures are not the people. I changed the pictures, so show the link doesn't look like that. Okay, Fangout absolutely doesn't look like that. Okay, but yeah, these are real names, and this is what the system thought they were going to recommend me to connect. So there's one person from LinkedIn. I don't know the first one, so that is not we didn't do a good job there. third person I met him at a conference, but don't know him very well. So still a lot of room to improve if you're thinking about a career change. Feed recommendation, right? So this is also something which we show on the LinkedIn page. If you go to our mobile app, that's the primary way for us to distribute content, similar to Yahoo front page. This is the Firehouse for LinkedIn. This is the Firehouse for Facebook. Right? What you recommend on the newsfeed, which is important. And the beautiful thing about the newsfeed is you can actually recommend many different kinds of content. It's not just recommending one type. Like you're not just recommending movies or just recommending ads. You can recommend many different things. Right? You can recommend network updates. Right? And that's where the social connection becomes important, the one which I was alluding to earlier. Right? So if you're connected to 10 friends, and if they've changed their jobs, or if they've completed a job anniversary, or if they have connected to someone else, or if they've been endorsed for something, or if they've uploaded a new photo, these are all content that I can show to this user. It doesn't necessarily mean I have to always show these, but these are candidates, items which I can show to this user, right? To keep them informed, to help them nurture their network. Okay? Then, if there have been articles written by an influencer like Deepak Chopra or Richard Branson you are following, those become candidates to be shown to you, right? If there have been an article in TechCrunch that has been shared by your friends, that's another candidate which I can show to you on the newsfeed, right? If you're following a big data channel on LinkedIn, and if there is something new that came up in that channel, you can show it to you. Channel are the topics. You can follow the topics on LinkedIn. Right? If you're following a company like Microsoft, and if the CEO gave an interview saying he's going to change the whole company, which I'm really excited about, that can also appear on the newsfeed. If there is a jobs, if we figure out you're actually in the job market based on your activity on LinkedIn, and there is a job which is germane to your skill set, that could also be shown. And finally, we also show ads. Right? So Stream is a distribution channel where we can kind of show any kind of content which we really like, as long as it engages the user, makes them come more often to the site. Right? And this is done by both. And so you can imagine this is a much more challenging problem than the ones which I previously described, because you have multiple different kinds of content you can show. You have to worry about diversity. You have to worry about the balance between social and non-social content, and so on. The utilities are very different. A click on a social update has a different value than a click on an article which takes you to another page and you read the article, and so on. So how do you balance all these different objectives? What is the objective? What are the utility values? Many interesting problems. Okay? But nevertheless, at the end of the day, it is still a recommended problem. You have an item pool and you want to recommend the best one to the user to maximize some objectives. Okay? Okay, and this is again an example of a jobs recommendation. And you might be wondering, why was this not the first slide and why is this the last slide? That's because LinkedIn is not all about jobs. LinkedIn is about things. I hope I convinced you of that, right? But yeah, if you go to the jobs page, if you're really looking for a job, we also recommend you jobs. These were jobs recommended for me. I definitely don't think the second one is germane at all. I'm not sure if I'm going to take either of these, but yeah, still, these were recommendations. Okay, so the goal of recommendation at the end of the day, as you can see from the examples, is to be a matchmaker, right? It's a matchmaking engine, right? Once you to place, it strives to place the best context in a given context for every user visit, right? But matchmaking at scale requires automation. See, this is the key, right? Even a human can sit down and do a matchmaking for a few segments of users, by kind of looking at saying, okay, yeah, these articles are good for males, these are good for females, these are good for people in software, these are good for, but that can only be done with a small item pool and for very few segments. If you are on the web, where you have tons and tons of content created every single day, and you really want to personalize these things to every user, you cannot do it manually. Some manual interventions, okay, maybe you can use some labels or crowdsourcing and all that, but that cannot be the only way to figure out the best recommendation. You have to automate, and that's where That is how you reduce the cost to serve content to users. And that leads to more profitable systems. And that's why companies are willing to invest in it, right? And the best way, which we know today, is by using machine learning and optimization. Right? And that's why machine learning is hot, because it reduces your cost to serve these content on the side, makes it more relevant, increases the bottom line for the companies, and they're willing to invest in this area. Okay? Every single company in the valley. Okay, so but now say, okay, but how do I automate? What objectives to optimize? These are the questions which we will try to answer in the next of the lecture. So it's not very easy. Like, what do you want to optimize? Although it seems easy at first blush, well, just optimize the number of clicks. It's not that easy, right? Because at the end of the day, businesses care about some long-term objective, right? They want more people to be coming to their site in a 6-month period. They want the total pool of advertising dollars to increase. They want more people to sign up for the network. They want more people to apply. These are the kind of metrics they care about. Right? They really don't care about CTR. If you say my CTR increased to 200% and nothing happened to these metrics, believe me, they're not going to care about it. Okay? They're going to question your methodology. Okay? That's what they care about. And we have to formulate objectives. So first of all, it's hard to optimize those directly because these are long-term objectives. The feedback loop is too long for machines to optimize these things easily, right? So what do we generally do? We formulate objectives that are based on proxies, which we believe can move those metrics. Okay, like click-through rates, revenue per impression, and so on and so forth, right? And then these proxies are optimized by using large-scale machine learning. Okay, so there is a lot of work that has been done here. Tons of work done here. And I'm the guilty party too. I'm going to talk about most of the stuff here, right? But a lot of work has been done here, right? And this is an area where I believe we'll see a lot of action in the next few years. How do we come up with better proxies that are more directly related to the long-term objectives business cares about? Okay, that's also a machine learning problem. Right? It involves doing attribution and so on and so forth. But anyway, more on that later. Okay, so here are the algorithmic components which you will have in a typical recommender system. One is content filtering and understanding, as I was telling you, right? I mean, if there is content that is junk, that is spam, you want to filter it out right away. You don't want to expose even a single user to those content because that's going to impact your brand image in an adverse way, right? You don't want to do that. Then you want to do things like you want to understand the aboutness of the content, you want to understand topicality, you want to run LDA and all that nice stuff so that you can extract useful information which can be used to do a better job in recommending. Okay? User understanding, as I said, right? Behavioral, based on all the activities you've done in the past. Are you a sports junkie? Do you really like World Cup? Are you a baseball fan? How do you tease these out? The users will, in most cases, won't give you that information explicitly. If you get it explicitly, you're lucky, great. Then you are ahead of the curve. But in most cases, you will not get those information explicitly from the user. You have to infer them implicitly based on all their actions. And it's okay. These are statistical systems. You will make errors, but as long as you do a better job, and the false positive rate is low, it's still good, right? Their social network, right? Their interests. These are things you have to tease out from the data. Then the third component is scoring, right? Once you have figured out, once you understand content, you understand user understanding, you have seen how users have interacted with content in the past, can you come up with a mechanism to score the likely value of an item to a given user, right? And the scoring would consist of estimating things like CTR, the relevance, the revenue, and so on. And then finally ranking, right? So you come up with machine learning methods to estimate different kinds of scores. But at the end of the day, ranking is a more complex phenomenon. It is not something that is dependent only on one particular scoring mechanism, right? You can score articles using multiple considerations, right? Okay, well, is the article more likely to lead to a click? Or how do I make the feed more diverse? How do I ensure the content is fresh? So even if I have to lose some clicks, I want to make sure that the content I show on LinkedIn is fresh because I want the users to perceive LinkedIn as a place where they come to get the fresh content, not stale content, right? Just a perception issue, right? And maybe it's right, because in the long run that matters, but there is no way for machines to understand that in the near term, right? So you impose constraints like that in these systems, right? And there may be any other objective, right? So ranking is a more complex phenomenon, and it is very application specific, but scoring is something which you can automate through machine learning very readily. And then different applications can use these scores based on the objectives they have and do the ranking. Okay, so again, just a simple cartoon. This is how you're putting it all together, right? You understand item, you understand users, you get all the input signal based on users' interaction in the past. On the items, you get different kinds of interaction data, whether the user clicked on something, whether they liked it, whether they shared it, and then you have a machine learning system here that scores the items using different aspects, like the probability of click, probability of share, whether it is similar to the items, and so on and so forth. And then finally, you rank items using different considerations, right? Involves scorings, involves multiple objectives, involves business rules, and so on and so forth. Okay, and again, this is how it works, right? So at a high level, you have a user, you have a context, you have an item inventory, you use an automated algorithm to select items to show, you get feedback, continuous feedback, you revise your algorithms, you keep doing it over and over again. And the goal of the recommender system is to come up with a mechanism which is going to allow you to have nice properties of this process. Right? You do things over and over again, you serve billions of articles, or billions of items in a given day on many of these portals. At the end of the day, when you look at the overall statistics, is that in fact your business or not? That's how you would design the system. Okay? Okay. And so here's the high-level picture from an architecture perspective. You get an HTTP request going to the server, and then the server has some item recommendation system running at runtime. Thousands of computation has to be done in a few milliseconds, sometimes in a few seconds, depending on how slow or fast the site is, right? And it gives the results back to the server, which then renders the page. Rendering the page is just not based on the results. If it goes to the front-end service, the front-end does some decoration and puts it all together nicely in a packaged form. Right? So the UI does matter. Right? Again, I'm not saying the UI. The actual content you're serving matters, but the UI also is important. Right? If you show content without doing good UI, sometimes it has a bad impact on the system as well. Right? So the user interacts. In this case, either the user clicks or does nothing. That data gets recorded in some databases, it goes to the cloud, and then it kind of badges this data up to, in some epochs, 30-minute, hour, 2-hour, again, depending on the application. It kind of gives it back to the statistical machine learning algorithm, the models get updated, the recommender gets updated, the computations change thereafter. So this was more a cartoon. This is what a real system looks like. Again, I've oversimplified some of the things, but roughly these are the components, right? So you have users coming to the web server, right? And then there is a ranker sitting here. Then there is something called an item retriever. It retrieves item from either an item index, right? So there is an index of items. There is something that injects the item and it indexes it. And the retriever at runtime, based on the user who's coming, retrieves the corresponding items, right? So for instance, if the ad has been targeted to only males, it will only retrieve, if a male is visiting the site, only items that are germane or that are important for the males will be retrieved, not everything else, right? And then there is a model store, right? So these are all the storage things, right? So this is the store where you store all your models, right? And the ranker calls these models, serves the item, it generates data. The data again goes back to different systems, some online, some offline. The models all get updated, the model store gets updated. New items comes in, they get injected, and the process goes on. Right? As you can see, there are so many different engineering components interacting with each other. Machine learning is only one of the things here, but a very important one, right? And all the system constraints, latency, these determine what kind of machine learning algorithms you can run, right? You might have a very fancy machine learning algorithm, but you cannot compute it at runtime. It's not going to work in the system. You have to come up with an approximation which will help you score items at runtime in a few milliseconds, right? Maybe hundreds of milliseconds, not more than that. Okay, so sometimes you are constrained by that as well. Okay, If you have thousands of articles to rank at runtime, then the amount of computations you will do will increase. So either you do parallelization, you do, you have to work with your systems engineer, and you have to iterate on the algorithm side to kind of make it all. Okay. So some important factors that impact recommender system, the items, like what kind of items? I mean, that's obvious. What kind of context, what metrics you optimize, the size of the item pool you have to rank from, right? Is it a very small item pool which you have to select from? Is the item pool more ephemeral, or is it more static over time? If it is static, then you can collect tons and tons of data for each of these things, and you can do a much better job after a while. If it is ephemeral, then before you collect data, it all goes away, right? So you have to be really reactive. If the number of articles is extremely large, then that's a very different problem, because the sample size per article required for you to estimate the quality or the score of these articles reduces considerably, right? So then you have to really come up with better machine learning methods to scale this up, and so on and so forth, right? Properties of the context, as I said. So one thing which I would like to specify on the property of the context is whether it is a pull model or a push model. So what do I mean by that? If you go to web search, the user is specifying a query, right? And the user is expecting to get content that has very good recall. But if you go to portal's web page, you're not really expecting a particular kind of content, right? You want to be pleasantly surprised by the quality of things you see there. So very different thing, right? In one case, in the case of web search, recall is very important. In the other case, precision is very important. It's okay if you miss out on something, but whatever you show should be of high quality, because the user is expecting to be surprised, and you cannot show a junk article there. But on web, if I'm searching for hotels in CMU, and if you don't give me the best one, then I'm going to be involved. The recall is very important. And that's why the problems, the search problem and recommendation problems have become a bit different in that sense. What kind of feedback you're getting? Are you getting explicit feedback, implicit feedback? Both that determines what kind of machine learning algorithms you have to do, right? What kind of business rules and diversity rules and editorial voice rules you have, what kind of objectives you have, what kind of metadata you have available. These are all different things that impact solutions. Right. So, and finally, the scoring, right? How do you score an item? For simplicity, let's assume we are estimating CTR as our score, right? Click-through rate of an article. Now, I want to emphasize that this is not a supervised. It might appear that this is a supervised learning problem, right? We have a lot of historical data, right? You've seen users interact with multiple items in the past. Let's say on the Yahoo Today module, or on the front page, or LinkedIn Today module. You collect all the data. You run a logistic regression, or decision tree, or neural net, and that is going to help you estimate a user's interaction with different items. You just score them, you're done, right? That's intuitively looks like that is what's going to happen, but that is not the case, right? Because in recommender systems, you don't have to be at the mercy of others to tell you what data to use for your training. You can intervene into the system and collect the data you want to do the training, right? Think about it. That's very important. You can intervene and you can run small experiments. For instance, if I have 40 different articles, I can take a small amount of traffic and do a random experiment on that small traffic, right? When a user comes, I'm going to flip a coin, select 1 out of 40, show it to the user, and see what happens. It's a small population. There's no problem in doing these experiments. And that can give you valuable data to improve your supervised learning algorithms. All right? So here is an example of why this is important, right? Very simple example, right? So you have, say you have 2 items, right? 2 news articles, right? The CTR of first one is, let's say, 2 in 100, right? So you've shown this article 100 times and you got 2 clicks. The second item has been shown 10,000 times and you got 250 clicks. Okay? So naively you will say, well, I know the CTR of this is better than this, right? The mean estimate of this is better than this, so I should show this article to all the other users who come to the site. This should be just removed. As long as this item is alive, this should not get shown at all. But this is not a good strategy, right? Because on a good day, this 2 could have been 4, right? So there is a lot of noise or variance in this estimate, right? Because it's based on smaller sample size compared to that. Okay? So the true CTR estimate of this article could be way higher than this. Okay? And by prematurely removing this article from the pool, you may be losing out on a good opportunity. right? So if you look at the curve, the probability of this item being better than item 2 is finite, right? So you keep experimenting a little bit with this item until this blue curve either moves to the left, and then you're absolutely sure this is worse than the red one, or it moves to the right, then you're sure that this is better than the red one. At that point, you stop experimenting, but until then, you have to continue to do some small experiments in the background to understand which one is better and which one is not. Now, this is 2. Imagine I give you 10,000 such things. Well, even if you're running small experiments with each of these articles, the amount of experimental traffic suddenly increases a lot. How do you do more prudent experimentation to figure out what is the best article? So this is a very different problem than supervised learning in that sense. Supervised learning is important because it helps you reduce the dimensionality of your problem. But at the end of the day, this is what the problem is, right? If you take away your ability or the luxury of doing experimentation on the web, then you will reach highly suboptimal solution. Okay, so in the rest of the talk, you'll see me go through a lot of supervised learning methods, but I want you to remember this important fact. Okay, then other factors, how do you evaluate recommended system, right? So before you even deploy a new method, how would you know whether it is good or bad? As I told you, it's an experimental design problem. It's an explore-exploit problem. So all the metrics which you have for supervised learning, do they apply? Maybe not. Maybe yes. And I'm going to talk about that later in the lecture. Post-deployment. Once you've deployed, how do you measure whether it's good or bad? So that is not that hard. You can run simple A/B tests, right? You have a control group which gets the status quo, gets the recommendation as it is getting today, and you create another treatment group which starts getting recommendations in a different way according to a new algorithm. And then you compare the metrics, right? So that's usual experimental design, which was done in statistics long time ago, and it is practiced quite routinely in clinical trials, for instance, and the same methodology applies. Okay. So before I go into the scoring, before I go into how we estimate scores like CTR, I would like to pause for a few minutes and see if you have questions so far. Any questions? Don't hesitate. Come on. This is your chance. Okay? Yeah.
You earlier mentioned about search and recommender system and how they are different. You mentioned precision and recall. But I always thought that both precision and recall are important for search. Search uses NDCG, which is some sort of an F score. So can you explain that a little bit better?
Yeah, so that's correct. Both precision and recall is important, right? But as you know, right, when you're doing a precision recall curve, the decision point has to be somewhere, right? And the question is, where should you draw that decision point for different applications, right? So on one extreme, you have the search problem, right? Where you have a query and the user is expecting the most relevant answers for that query, and you can't miss out on some of the obvious results, right? And that's an example where recall is extremely important, right? You cannot miss out on a very famous hotel in Pittsburgh. Then it's not going to look good. Your search engine is not going to look good. On the other extreme, the user is just coming to the front page. You have absolutely no idea they're coming from. They're just coming there. They're expecting something interesting to read. And if you show them something junk, right? That's not a good user experience. Right? So precision is important, of course. Without recall, you would not even be able to pick up the best things in most cases. So you need a good item inventory, but it is better to filter out something of low quality than to show. And then most other applications are somewhere in between, right? Sometimes you may have a user coming to the portal with some contextual information. Like for instance, on LinkedIn, if I visited the jobs page and then came to the home page, I know you're looking for a job, right? And I might tailor my recommendations based on that information. So that is giving you some context, not a perfect one, but some context, right? And so most of the applications are somewhere in the continuum in between these two extremes. But that's an important distinction to make when you are actually doing these algorithms. The recommender algorithms are not about taking an item pool and running machine learning on that. I think a lot of decisions have to be made before that happens. Before you decide what is your item pool, how to decide what your item pool should be is a very important component of recommender problem. Because at the end of the day, if your item pool is not of high quality, no matter how well your machine learning algorithm does, it's not going to serve good content. So that's the context I was kind of alluding to that.
What do you want to do this kind of recommendation and process?
Okay.
Okay. So what do you want to do this kind of recommendation and process at runtime? So it's like a best effort, or what if you do, for example, multiple recommendation, it takes time to capture?
Good question. So the question was, if you are doing so many complex things, how do you manage to score things at runtime with tight latency constraints? So first of all, that's the challenging problem. And again, many of the methods I will talk about later, you'll see how that works. So what ends up happening is you do computations in different stages, right? There are some computations that can be done offline to estimate parameters which are stable. They don't change over time. So you can do it once a week on Hadoop and to store them. Then there are some computations which you can do near real time, right? So every 30 minutes you fire computation. And at the end of the day, these two computations should give you enough things that can be computed very quickly at runtime. Okay. In many cases, people do two-pass ranking, right? So even though you have a complex machine learning model, what you can say, well, since my item pool is too large, I'm going to use a simpler model to reduce the set of computations that have to be done for the second model, which is the more complex model. Right? So your 10,000 things, you narrow it down to 1,000 things by using a very simple model, popularity. Which article is more popular in terms of CTR? Reduce it to 1,000, and then re-rank those 1,000 by using a more complex machine learning model. So this is just a tactic to scale computations. It is not optimal at all, but it is a tactic to scale computations. So those are the kind of things that are done. Right? And so the machine learning models which you create offline has to take that into account, right? If you create a very nice machine learning model with very great metric and you can't compute it online, then it's of no use. But you have to be cognizant of that. Right? So compute time is important as well. And so all the work we are doing in scalability and other things are extremely important for these systems. Okay, so let's move on. So I'm going to talk about how we score user item interaction. For instance, how do we estimate CTRs in most of these web applications, right? So first of all, we get lots of data from each of these applications, right? If you look at Google, Facebook, LinkedIn, Twitter, huge amounts of data, very high frequency, huge amounts of data, right? And you may ask the question, like, well, if you have so much data, do we really need to bother about this problem, right? We all learned in the past that statistical modeling is the art of doing modeling with small amounts of data, right? You just don't have enough data to estimate your parameters. Now I am in the world. There's so much data, so why is this a hard problem? Well, not quite, because you'll see the number of parameters you need to learn increases with the amount of data you get. The more data you get, there is more heterogeneity in the data, right? If you're building a personalized model per user, the more users you get, the more parameters you need to estimate. If every user requires estimation of 2 parameters and I add 1 million users, well, I have 2 million new parameters to estimate, right? So the dimensionality, the curse of dimensionality is not reducing with the arrival of new data at all, if you want to do a good job. Okay? The system is dynamic, often, right? The web is dynamic. It changes, right? You cannot use all the data in the past for everything, right? Maybe something is more time sensitive, non-stationary, so you can only use the most recent data. And rapid learning and quick reaction is important for such applications. Data sparseness for personalization. So this is what I was alluding to, right? If you think of user item interaction data as a matrix, user item matrix, these matrices are very sparse, right? Only 1% of the entries or less than that are filled up in practice. And moreover, if you look at the distribution of user visits, they are power law. What I mean by that is a small fraction of users visit a lot, and then there is a big mass of users who visit the site very sporadically. And similar things for items, right? If you have an item pool, there will be some items which will be of very high quality, so they will be shown a lot, and then the remaining items will not be shown that often, right? So you have this two heavy-tailed distributions interacting with each other, creating a lot of data sparsity and imbalance, right? So if you look at the entries in these matrices, they're not distributed randomly at all. Contrary to the assumptions that are made in many matrix distribution theorems and other things, they're not distributed at random at all. They're distributed in a very imbalanced way because of this power law behavior of data. Okay, so that makes it more challenging. Okay, so I guess so now you might wonder, okay, well, is this a hopeless problem? Can machine learning help at all? Well, of course it can. That's why we're here, right? So some grouping behaviors in your data are more stable. For instance, the fact that users in San Francisco tend to read more baseball news is roughly true. It's probably not true for every single San Francisco user. It's probably not true for every single baseball article, but in general, it's true. Right? That immediately puts you above random. Okay? And so now the key is, how do you model these group behaviors? Right? How do you tease out such groups from the data? Right? There are so many different ways you can slice and dice the data. What are the right grouping structure which you need to come up with to estimate these patterns, right? And that's the bias wave experiment, which we all know from machine learning. If you build more coarse models, they will be more stable because you have tons and tons of data to estimate those coarse models or few parameters which are using a lot of data, but they will not generalize that well. Right? If you build very granular models, then it will be unstable. It won't be very good, right? Because you have high variance estimates and they may not generalize well either. So the sweet spot is often in between. And that's why, nowadays, the passion is to build very granular models but do regularization. Right? And that's a good way of dealing with heterogeneity in your data, for instance. Right? And again, as I said, another advantage is you always have the ability to run experiments. So this is the key thing. If you find that the data you have at your disposal is not good enough to help you make decisions of serving the best things to users rapidly, you can always intervene and run an experiment. Like if you don't know with high confidence whether San Francisco users tend to read baseball news, you can run a small experiment, take a small random sample of users from San Francisco, show them many baseball articles and see what happens, and you will know it. You have the ability to do that. But how to do that at scale is the question. That's why you need machine learning and all the nice theory behind it. Right? Because one or two experiments is easy. Okay. The supervised learning to reduce dimension, experimental design to collect better data. These are the two main things. That's why it's an explore-exploit problem where supervised learning helps you reduce the dimensionality. Okay, so this is a rough cartoon again. Right, so you do all these feature construction, you build offline models to capture all the stable characteristics, and these are used to initialize near online models that are more fine-grained models, and that apply corrections at very granular resolutions, like at the user item resolution. And behind the scenes, you always have this experimental design or explore, exploit, or algorithm running to give you the right data to build good models from both these components. Okay. Okay. And so again, another thing I want to emphasize is the kind of machine learning models, the kind of strategies you need will depend on the kind of problem you have. So if you have a problem with very low number of items versus a problem with very high number of items, the strategy will be very different. Right? And we'll see that later. But yeah, keep in mind, it's important to understand your problem first before you go for a solution. Okay? Oh. Okay, this is not okay. It's not a good slide at all. Right? So it's a self-promotional slide, which is not important. What is all these? Okay, so now, in order to give you more intuition, let's look at a very simple model. Okay, suppose you have an application with one single slot, bunch of articles or items, and all you want to do is rank these articles by popularity. Okay? Popularity is measured by the CTR of that article, global CTR of that article. All right, and when I say global CTR, I mean the true CTR, not the estimated CTR. True CTR. Okay, how would you do that? So, although this is not sufficient for many applications because they have to personalize, as we all know, but it is a good baseline to be used for other sophisticated methods. In applications which you were talking about, where the computation can become very heavy, these methods could be used to reduce the initial big content pool to a smaller pool and then go the re-rank. Right? So these models, although they are simple, do have their utilities in real systems. Okay? So if CTRs were known, of course, there is no issue, right? You just know the CTR, you just rank order by CTR, you're done. But the crux of the problem is, you don't know the CTR, right? Okay, so let's look at this problem, right? User visiting the site, you have a bunch of articles, you show an article, you get a response. What item should you select? Right? That's the decision you're making, right? If you're a web server, that's the decision you need to make. how would the web server think about making this decision? Should it just select the item which has the highest predicted CTR so far? Or should it think about showing an item that can potentially best, but we need more data to decide? Remember that curve which I was showing. You're not certain whether it's good or bad. There's too much uncertainty. Should I show that user one of those articles? Because I need to converge to a decision fast. Otherwise, I will be lingering for too long and the opportunity would be lost. Or should I just show the article that has the highest predicted CTR so far? And this is an article which I've showed numerous times in the past. Okay, that's the decision you have to make. And so the first one is called the exploit phase. You exploit what you have learned so far, right? The second one is explore. Should I explore more to make the system better, right? So that is where you're doing experimentation. Although you don't know it, but you're doing experimentation as you go along, right? Continuous experimentation. Adaptive experimentation, right? So that's why it's different, right? So again, this is an example. So again, I'm showing you a real example. This is actually running on Yahoo. It was running for a long time. I don't know what is running now, but it was running for a long time, right? This was one of the first algorithms we did to improve the Yahoo front page recommendations, right? So the item pool to be shown on the Yahoo front page today module is editorially created by the editor, right? The humans, editors, who look at a bunch of articles from the web and say, these top 40 are the ones which should be shown on our site at this moment. They do all that curation. And again, this brings back to the high precision thing just talking about, right? And so what I have here are curves that were obtained. These are CTR curves or articles that were obtained by using a randomized experiment over a period of 2 days, right? So you can see this article started here, and it was really doing very well, but the editors decided to take it out of the pool. Why? Because it was not fresh anymore. Although it was still doing very well, they thought it was not fresh and it is not consistent with the brand of Yahoo, so it was taken out. And again, if you think about it, it's not inconsistent with what we are doing here, right? Because CTR is not reflective of the long-term utility of the system. There are many other constraints that combined with CTR helps you realize the long-term utility of the system. And in the absence of science that can do it perfectly, such interventions are only natural. That's what happened here, right? So yeah, you can see there are a lot of different. Each curve is an article, and the CTRs are non-stationary over time. The articles are short-lived. There is huge temporal variation, and so on and so forth. So that's the challenge, right? So given this kind of data, how would you select the most popular article at any given point in time? Right? We ran the same experiment on LinkedIn today, and surprisingly, the two problems are so similar. It's just amazing. I didn't believe it when I saw it, right? Oh yeah, I went to a new company, the same problem. It's just so rare to see, but it is exactly the same problem, right? Even the curves look very similar, although the previous one I did a moving average here, I didn't, so yeah, it is pretty similar. Okay, so another thing which you will notice in these systems is if you show the same article multiple times, the CTR keeps going down, right? So every pink curve here is an article. This is the CTR, relative CTR drop if the same article is seen twice by a user, thrice by a user, and so on and so forth. So if you keep showing the same article multiple times, with every repeat view, the CTR on that article for that user goes down. This is a fact, and this is extremely important. It is there in every single recommended problem on the web. Users get bored, they just show the same article multiple times. And many of them will not react to it. I told you I don't like it, why are you showing it again? That's really, yeah, what's going on? And the reason some of them still click after seeing it for the 5th time is because they didn't see it the first 4 times. They were doing something else on the web. That's the only reason why you see that. Okay? Okay, so here is a very simple algorithm which you can run, and actually it's very effective. So first, this is again just to estimate the popularity. Very simple, right? So you take out 5% or say epsilon % of your traffic where you randomly show articles to these users, right? You randomly select 5% of users, and for each user visit by the cohort in this, by a user in this cohort, you randomly flip a coin and select one article at random and show it to them, right? So this is what we can call your explore pool, right? You're exploring every single article in your pool by doing this randomized experiment, right? And then You do all your popularity estimate and all that by using this data and the rest. And then the remaining users, when they come to the site, you just show them the article that has the highest click-through rate at that given point. Okay, so this is a very simple explore-exploit scheme. It's also called epsilon greedy explore-exploit in the literature. How would you take care of temporal smoothing? Well, you saw the CTR change over time, so you have to incorporate the temporal aspect into it. And that you can do by using regular methods like Kalman filter and moving average. I'm not going into that. You also have to discount the item scores for repeat views. So based on the curve which I was showing you, a user who is seeing the same article for the 5th time, the CTR should be discounted to half. So I know the popularity of this article for a user who is seeing for the first time is 5%, but now since you are seeing it for the 5th time, it's 2.5%. Right? So you learn those factors from the data and just discount it. And if you just run this algorithm, it's not a bad recommendation algorithm. It's a very good baseline algorithm. So this is one way of solving the most popular. Right. And again, I think I'm just showing you some a way of doing the Kalman filter. But again, I'm not going to go into the details of these things. There are many other methods of smoothing curves, time series curve. I don't want to go into that at all. But you can pick up any one of your favorite and do it. But I picked up the Kalman filter, but that doesn't mean you have to do it. All right. These are more details. You can read it offline if you want, but not very important, right? So what I showed you was a particular explore-exploit scheme, right? You carve out a small fraction of traffic and do random exploration, and then do exploit on the rest. That's not the most efficient. You can imagine, right? I mean, you might end up either doing over-exploration or under-exploration, right? If you take a small fraction to do your exploration, you're under-exploring. You will be slow to react. If you take a big traffic, then you're over-exploring. So how do you do better exploration? And so that's where the explore-exploit problem really comes in, and it's also called it also has strong connection to what is called the multi-arm bandit problems in the literature, right? So at a high level, the problem is as follows, right? Suppose you have a gambler and you have 1,000 plays. What is the best way you can experiment to maximize your reward, right? So you have 2 slot machines. In reality, this slot machine has a higher payoff than this, but of course, as a gambler, you don't know what it is. Right? You start blind. You have 1,000 plays to make. What is the best way for you to experiment to maximize your expected payoff? Okay. So you can think of the slot machine as articles, and the gambler as a user. What is the best way to experiment with these articles to maximize their overall click-through rates in the system? So similar problem, right? And we are going to see more results later on. Okay, so I think with this, we have reached the point, we have reached the end of the first section. We probably can take a 2 minutes or 5 minutes break and then come back. And feel free to catch me during the break if you have questions.
Right.
They're on the other times, yeah.
Right. So you're probably also working a lot with India, right? Also,
I decided not to really make a mistake once. Yes.
copy and they actually grab
I don't know. If you also, I guess whereas if it's 9 o'clock in the evening, I'm sitting in the classroom and very and then I think search and
no, es para los orales. Es mío, pues,
So, I need
Okay. Okay, nice.
Okay, everything in that table.
Do we still have any 9-volt batteries around that are not busted?
For the room,
9-volt.
we should call them and they call them in like 5 minutes.
Okay, so then let's.
Welcome back. So what I'm going to do in the next 1.5 hours we have, I'm told we can take 10 minutes for learning, so 1.5 hours. So I'm going to talk, as I was telling you, right, there are offline. At the end of the day, the recommender problem is to do all these rank ordering computations at runtime. Right, and as I was telling you, the latency constraints do not allow you to do a lot of computation at runtime. So often the strategy that is adopted is you do some computations offline, very sporadically, once a week, once a day. And then there are some near online computations which you do, maybe every 30 minutes, 15 minutes, and then finally you do some computation online, right? So I'm going to talk to you more about some offline methods first. That is going to be, that is generally used to capture the stable characteristics, right? Like users in San Francisco liking baseball news, those kind of things. And then online models, right? So this user from San Francisco does not like this article about baseball, those kind of computations, right? If you know about it. And you know, in many cases, you can seed your online methods by using some information from offline. So those are all the initialization methods. Finally, of course, explore exploit. How do we do these experiments? I showed you a simple explore exploit for most popular, but as you saw, you know, those methods may not scale very well to very large content pools, and you have to do a lot of experiments. So how do you scale those experiments? So let's begin with the scoring method. So first, let's talk about classical methods. So first of all, a lot of this stuff will be covered in Javier's tutorials. So I'm going to go through them very quickly because you hear a lot about them in that tutorial. I'm going to focus more on the other part. Right, so this problem is clear. Users visiting a website, and you have a bunch of items, and you show them, and you get response, and then you predict based on these responses. You have to predict the other entries in your matrix. Right. So this is the input to most of these systems. What you know about the items? Let's call them item features. Right. The keywords. If it is an article, you know the keywords. You can represent them as a feature vector. And then you know the topic of the articles and so on and so forth. How many of you are machine learners here? Okay, okay, not too many. So what? How many of you have other backgrounds than machine learning? And, you only know elementary machine learning, not too much beyond that. Okay. So it seems like there is a intersection that knows something in between, or they are too shy to admit they know a lot. But anyways. Okay, so if you find that I'm saying something which is too advanced or too dumb, too preliminary, just raise your hand and I'm going to either go fast or slow down. Right. So then you have users. So you also have user features, right? So for LinkedIn, for instance, you know all the information about the user from their profile. We see who they interacted with in the past. So all the social network. We know where they are visiting. If you're visiting a job page, then I know that there is a strong intent as far as finding a job is concerned and all that. So that's all represented as a feature vector for user, right? And these feature vectors could be very high dimensional. It could be thousands of dimensions, right? Binary bits, right? Do you like baseball or not? Many binary bits, right? And then you have users' fast response for items, right? So you're optimizing the Yahoo Today module or LinkedIn Today module or the LinkedIn feed. You have seen users users have visited in the past and they've seen items and you've seen how they've interacted. Did they click on it or not? And those kind of information is all captured in that vector Y, right? And so the scoring method, which I will talk about, will be feature-based. So just by using the features of items and users, how do you predict the CTR of a user for a given item? So this is good for cold start. What do I mean by that? If you take a random user who has never visited the site, if you take a random item that has never been shown in the past, you can still capture their features. And that alone would let you predict what the CTR would be of that item for that given. Right? So without that user seeing anything before, just based on their feature values, you can generalize and say what this user is going to do for that particular. And then I'm going to talk about collaborative filtering. So collaborative filtering only uses the past ratings of users on the right. So it does not use any features at all. Only based on what you've done in the past from the today module, I can say what you're going to do in the future. And then finally, hybrid approaches. How do you combine the good and the bad of both collaborative filtering and feature testing? Okay. And so some scoring methods, as I said, I'm going to breeze through this. So there are some supervised methods which are unsupervised, does not use the response data at all. Right? Whatever users have done on the today module is not used at all. You just use the user features, item features, and compute some similarity score. Right? So cosine similarity, Jacquard for binary weights. There are many other IR methods like DM25 and so on and so forth. And then you can also do supervised learning methods. So you can say, well, the similarity between user and item based on the feature is given by this quadratic function. And you can see the A's are something that have to be estimated from the data. So these are unknown parameters, and you can estimate them by using standard supervised learning method. Right? So you kind of posit a probability model that generates your data given all the information you know about the user. And of course, if the parameter space is very high, you regularize them by using some penalty function, and you do an argmax of that, and you get it. Right? Standard machine learning. So that's why I was asking that question. How many of you have it? But I'm assuming if anybody doesn't understand that, raise your hand. Okay, this is called utility elicitation, right? So I think, so I'm assuming everyone knows machine learning very well, right? If you understand that, right? I'm going to go fast. Okay, so then this is not necessary. You already know this, right? So one way of doing supervised learning is if you have binary data, you have 0, 1, you can write a Bernoulli model, and this is what it looks like, and this is what the loss function looks like, and you can optimize that using the previous formula, and you can get the A matrix. Right? And that gives you similarity function between user and items by using the ratings data, the response data which you've seen in the past. So this is generally more accurate than doing unsupervised, of course. Okay. Collaborative filtering, it does not use any features. It only uses users' past ratings. So there are methods based on user, item similarity, matrix factorization. So here is an example of how you would use user similarity to predict the user I score on item J. So user's I score on item J is the average rating by that user, and then this is the similarity of user I to a user A. And how do you compute that similarity? You look at what items have been responded to by user I, what items have been responded to by user A, and you compute some similarity measure based on either Pearson's correlation, Jacquard, and so on and so forth, right? And this is how user A rated item J, and again you just normalize it by the average rating. So you just detrend the data based on the average rating, right? So as you can see, right, your rating on item J depends on your average rating, and it depends on how users who are similar to you rated that item. So that's why it's called user similarity. And you can turn the equation around and do item similarity. There are methods that do both user and item similarity, and so on and so forth. It does not handle cold start very well. If there is a new user who has never rated anything at all, well, first of all, you can't even compute that user similarity to any other user. So you're basically stuck. You can't do anything. You have to just randomly show things to this user until you get enough ratings, and then you can start picking it up, right? So cold start is bad. Warm start is very good, right? If you've already given me a lot of rating, I can use all that to do this very well, right? And more of it in Javier's presentation. Okay, so recently matrix factorization has also emerged as a method of choice to get these user similarity and item similarity. As you can see from the previous equation, this is not a very elegant way of computing user similarity and item similarity, right? I mean, you're using Pearson's correlation, but sometimes if you look at two different users, the number of items they have rated could be 2 or 3. Estimating Pearson's correlation based on 2 or 3 items is not a very good idea. It will incur a lot of noise and so on and so forth. So how do you do a better job of estimating the similarity? So it turns out matrix factorization methods provide you with a very nice representation of including both user and item similarity into a single model. This is how it works. You map every user to some latent dimensional space, some small latent dimensional space, 10 or 20. Right? So every user has a representation, I'm calling this UI. Every item has a representation, I'm calling that VJ. And then you say, deposit a model. You say, okay, well, the similarity of the rating of user I on item J depends on the inner product of the user to the item latent vector. Right? This is the angle, the cosine of the angle between these two vectors in the same latent space. Right? And the trick is, how do you estimate these latent representations? So you estimate that from the data. Like if you have a Gaussian response, then you can just do that by minimizing this loss function with some regularization approach to control for it. So this is matrix factorization, and implicitly what it is doing is it's doing a better job of estimating user and item similarities in the same frame. That's what it is doing. You can have other models to estimate similarities as well, but this is a representation that has caught on, and it has caught on mainly because of the work that was done in the context of Netflix competition. These methods were extremely successful there, compared to the traditional methods. Right? But again, more of it later in the other tutorial. And then there are hybrid approaches, right? So you know that collaborative filtering is So how do you combine the feature-based method and the collaborative filtering method, right? Because one of them is good in cold start scenarios, the other is good in warm start scenarios. But in order to really run a good system, we need to have methods that can perform both in cold start and warm start. So how do we do that, right? So there have been several heuristic approaches that have been used in the literature. So for instance, one option is to just use a linear combination of collaborative filtering and content as they are called, content-based method or feature-based method, right? You get a prediction from a feature-based method, you get a prediction from collaborative, you just do a weighted average from that. Right? With weights trained offline using some data. That is a problem, right? Because in many cases, the confidence you have in the collaborative filtering estimate is much higher than in the regression estimate, and vice versa. And so the weighting should depend on how much confidence you have in the estimates of these two different components, right? If you have a very precise estimate based on collaborative filtering, you should just go with that. You should not depend on the feature at all, and vice versa, right? So those methods cannot do that. They just use a global weight, and that is often not very sufficient for most of the application. The other method that has been used is you use the content method to fill up your matrix and then apply collaborative filtering on top of that. Right? Two-pass method, right? I mean, these are early methods. Filter mod. There is also something called filter mod. So what you do is you add the features of users as additional pseudo users in your matrix, and then you collaborate. Different styles, right? Recently, there have been work done more on a model-based approach, right? So, can you write down a probabilistic model that can combine the goodness of both the feature-based methods and collaborative filtering? They are generally more precise if the model caters to the assumption, if the data caters to the assumption made by the model. They're way more precise, but you have to be careful of what kind of assumptions you're making in your probabilistic set for this to be successful. But I'm going to talk more about that later. Right? Okay, so since Javier is going to cover the rest of the thing, I'm going to cover more the model-based approach of combining these two methods. Okay. Okay, so let's begin simpler first. Again, I'm going to do binary response. So think of click, no click, Yahoo Today module. That's our primary application in mind, right? So let's think of that always. And what I'm imagining here is most users who are in our application do not come to the site very often, right? For most users, you'll only see 2 or 3 ratings in the box, right? So if you have an application where a large fraction of users only give you a small number of ratings, then you can come up with simpler methods to solve this problem, right? And we'll later see methods where that is not true. You can enhance this model to do better job for other methods. But let's imagine that's the case. Okay. So you have item j, you have user I, you have time interval t, right? And this is the response you observe. So you are assuming it's a Bernoulli model, and on the log R scale, you write down the model, right? So this component is the cold start component, right? It's capturing user's affinity to items, similar to the scoring function I showed you earlier. This is all based on features, right? So it's going to kick in when there is a cold start problem, new user or new item. And this component is capturing additional idiosyncrasies that are not captured by this component, but only at the item level. So as I said, right, I mean, I'm assuming I don't have enough data for users to capture their idiosyncrasies. Only the item idiosyncrasies is what is being captured, right? So this is a latent factor that is associated with every single item, right? And you're capturing the affinity of this to the user features. So if you have a million-dimensional user feature, this is also million-dimensional. For every single item, you have to estimate million parameters to estimate the idiosyncrasy that is not captured by the feature approach. So this is the first model that is, you can see how it's combining the cold start and the warm start, right? But only on the item side, right? So these are item-specific parameters, and now if you have million user features, you can't estimate million parameters for each item, right? So there has to be a way of reducing the dimension. So what you do is you say, well, I'm going to project those million-dimensional features per item into something like this. So you know, I'm going to take V and I'm going to write it as some global matrix B times theta, right? So this is million. This could be million by 10, and this is 10 by 1, right? So you estimate this global parameter million by 10 by using all your offline data, right? You can see, look at all your past offline user interaction matrix, and you can estimate this parameter. You can estimate B, you can estimate A by using the usual likelihood approach, and then all you're left is estimating 5 or 10 dimensional parameter per item when they come into the system. That's a much tractable problem than estimating million parameters per item. So that's one way of doing it. So this is combining both offline and online, right? These are all offline. These are all offline. This is near online. Every 30 minutes or so, you kick off a process, and when a new item comes in, you just update the data J's, and that captures residual idiosyncrasies an item may have with the user. Okay, now let's go to the more general case, right? Where you have users, some of which come to the site very often. You have items, some of which come to the site very often. How do you capture both the cold start and warm start, or how do you capture the residual idiosyncrasies that users could have and items could have to each other? Right? That's what we're going to talk about next. Okay, so first, yeah, I think I can skip this based on what we have done. Okay. So in order to do that, we are going to use latent factor model, right? And let me give you a brief overview of what that is. So as I was telling you when we were describing matrix factorization, you map a user to some latent space, and you map the item to the same latent space, and then you kind of measure the affinity users and items have with each other by looking at the cosine of that latent space. So the same thing here, right? So suppose there is a latent space, and let's, for the sake of simplicity, say this is two-dimensional because we can all see two dimensions. Let's say one of the dimension is how much affinity the user has to sports articles. The other dimension is how much affinity the user has with news kind of articles. Right? I mean, I'm just labeling them arbitrarily. They may not mean the same thing when you get an estimate, right? And so when a user comes in, for every user looking at all their data in the past, you have to map them to some point in this two-dimensional space, right? So for instance, this user, well, he's not that newsy, but kind of sportsy. Right? That's what you can interpret, right? Now you can also map a user to a Euclidean space. In some cases, you also map them to a simplex. Right? So there are two different representations. One is Euclidean, one is more simplex. Right? Simplex is okay, well, you're 50% newsy, but 30% sports, those kinds of things. Right? So this user may map here. Right? If you map them in the simplex, okay, well, he's not that newsy, but very sportsy, right? So 30% newsy, but maybe 70% sportsy. Two different representations, and they have their advantages and disadvantages, and I'm going to talk about that a bit later. And now we have a new item coming in, or an old item in the system, and they also get mapped to some point in the same latency, right? So either here or here. Okay? And now the user's affinity to this item is going to depend on the distance or the angle between these two things, right? So the affinity is captured by the cosine of the angles between this vector and this vector, right? In this case, cosine of the angle between these, right? So, and here too, right? The affinity is measured by the cosine of the angle between these two vectors. Here and that's the model representation. It is not enough, right? It is just telling you how the model is thinking about the problem. It does not tell you how they will estimate the parameters and all that other complexity. That's something which you have to go through in a minute. Okay. You may have seen this equations before, right? So every user has a latent vector. Let's call them UI, and this is the bias of the user, right? So some users are just too clicky than others, right? You just tend to click on everything I show you. Some users are more, they're more cautious in terms of what they click, what they not. And then similarly for articles, some articles are just way more popular than others, right? So that's why you have this beta J, and then this is the usual vector, and then suppose you have n users and m items, the expected value of the response maybe after some transformation. So if you're using a binary response, this t is the log odds function otherwise. Or Gaussian t is just identity, so the expected value of this response is given by this, right? So it depends on the popularity of the user, popularity of the item, or the bias of the user, popularity of the item, and the user's affinity to this item. Now in matrix factorization, you generally see UI transpose Vj, so V is not there, right? And you may wonder why is that the case, right? I mean, why can't I have a different dimension for users and items, right? Well, you can, right? I mean, if you write it in this way, you can. But empirically, people have found, but that this representation doesn't buy you too much. So it's better to set m and n to be the same and set this to identity and just do the problem that way. But you can try this. I have tried this in the past. It does not help much. It does not hurt, but it does not help much, and it's unnecessarily adding more complexity in terms of additional hyperparameters. But in some of the applications, it can help, and you can try that. There's no reason to have the same dimensionality both for users and items. But anyway, so this is the model, and again, this is the usual matrix factorization, and there is a lot of early work in this area on how to do matrix completion using this model. So Srigro did this first, where he was trying to do the matrix completion by minimizing the trace norm of the matrix. So it's a convex program, semi-rhythmic programming, not very scalable, and then they constrained the Frobenius norm of these factor matrices, and that was non-convex, but it was scalable. There have been papers that train ensemble of these things. So I'm not going into that literature, but there's a lot of theoretical literature on this area. Right? So Netflix prize, remember the Netflix prize? This is the model that was very successful. You kind of estimate these user item factors by using the squared error loss, regularize that, stochastic gradient descent, alternate least squares. The winners, eventual winners started with alternate least squares, but then they moved to stochastic gradient descent. Right? Just some history here. You can write this as a probabilistic model as well, graphical model. You have responses, ij, and they depend on the latent factor of the user and items that are drawn from some prior with some variance components, and that's what the model would look like. Right? So if you're familiar with graphical models, this is what this looks like. It can be written as a graphical model, and then there have been papers that have done Bayesian probabilistic matrix factorization. Essentially, what they have done is represented this as a graphical model, and then they have used the usual MCMC methodologies to estimate these parameters. And since this is a multimodal posterior, the kind of estimation you do, kind of fitting method you use, changes the answer. You don't get the same answer. Right? So, in particular, I have also played with this and found that if you use an MCMC-based approach, you do get better answers than if you don't. But of course, doing MCMC means you have to do more costly computations. However, nowadays there has been a lot of work done to scale up these computations, so it's not a big problem anymore. One other interesting thing I found about the MCMC algorithm is it is more resistant to overfitting. So what do I mean by that? Right? If you're doing stochastic gradient descent, some of these parameters like the A's and the learning rate, they have to be hand-tuned, right? So you have to do a lot of cross-validation and run a lot of things and figure it out. In an MCMC setting, you can actually get these estimates for free, right? If you run an EN algorithm, you're going to see how we do that later. You can get these hyperparameter estimates for free. So what we have seen is, if you increase the dimension of your latent factor, there is more shrinkage, right? So this A of U is determining how much shrinkage you have, right? So the more dimensions you use, the data tells you that you should shrink more, right? You can see that like the variance here, the prior variance here was 0.234, now it becomes 0.017 as you increase the number of dimensions. Right? So although you're using a lot of dimensions, the effective dimensionality reduces because you're doing more shrinkage, right? You're constraining the factors to be around a smaller ball of smaller ranges, right? And so what it's doing is for heavy users who have a lot of rating, it gives you more flexibility to capture their affinity to items. But for light users who don't have a lot of ratings, it shrinks the hell out of this factor. And you kind of get the best of both. So that's what is happening. And I think that's one of the reasons why MCMC works well, because it gives you automatic estimates of the input parameters. Okay? Okay, so now this is all about matrix factorization and why I was talking about that, right? So I'm going to show you how you can incorporate both post-start and on-start by extending the matrix factorization. By using a very simple idea, right? And if I tell you now, it's obvious, or maybe it is obvious. It was not being used, right? So the main idea is to change the prior mean. In matrix factorization, if you write down the graphical representation, the prior mean is 0. Now what you're going to say is, look, if you and I are both from San Francisco, and I know your factor estimate, and I know many other San Francisco users, and I know their factor estimate, my mean, the mean of my factor, latent factor, should be centered around the mean of San Francisco users' factors, not around 0. Right? Why should it be centered around this neutral value 0? Right? I can cluster my users based on features, and for every cluster, there's a different factor mean based on the users I've seen in that cluster. Right? So why not just have a separate mean for each user, depending on which cluster they belong to, based on their feature values? Okay. So users in San Francisco should have a different mean to begin with than users from New York, because we have tons of data about users in San Francisco and New York in the past. You know what their factor estimates are. You should just center them around that. Now, if you carry that idea forward, if I give you large feature vectors, you can still do the same thing by adding more regression kind of models in the prior, and then do the estimate. Right? So that's the main idea. Right? So it's kind of simple, right? So this is what it is, right? So this model is exactly the same. Now the only thing is, remember in the earlier case, alpha i's was centered around 0. Now it is centered around some regression function that depends on the features of the user. Similarly, the UIs depend on some regression function that is dependent on the features of the users and so on for the others. Okay. So you have to do matrix factorization. As part of your matrix factorization, you have to get an estimate of the G's and the D's and the little b and the little g. And so if you have a new user, their factor estimates are no longer 0 anymore, right? Their factor estimates will be given by this function of the user features. That's how you're dealing with the cold start problem. If I don't know anything about you, your factor estimate will depend on the features you have. If I know a lot about you, then your factor estimate will be similar to what you get out of the matrix factor. That's the main idea. Okay, so this is what the graphical model looks like. Okay. So earlier you saw that these were drawn from a prior mean 0. Now you have these additional G's and D's hanging out, right? And that's what it's to be estimated. Okay. Okay. So now, in order to give you more intuition, what is this going? So for Gaussian models, you can marginalize over the random effects, right? I mean, just integrate from your equation, just integrate out the random effects, and what you will see is that marginally these Yij's have a distribution which is centered around Mij and some variance sigma square, and this Mij exactly looks like this. And I leave it as an exercise for you to do the marginalization, but you can see that if you marginalize, then this model which I was showing you earlier does predict ratings based on the user and item features in cold start. It is no longer predicting zeros anymore. It is capturing the interaction based on the user and item feature. Right? So again, these are all technicalities. I'm not going to spend too much time on it. You can just sit down and read about it. You will be able to figure it out. It's pretty basic machine learning, but I'm not just going through all the math very rigorously here. Right? And I'm just showing you. So this is a plot from the Yahoo front page, and I'm going to show you the plot for only the first factor. We did a 10-factor model, but I'm showing you the plot for the first factor. So this is the factor estimate you get if you run a regression model. This is the factor estimate if you get if you run the new model, which I'm calling regression-based latent factor models. Not a great acronym, but just for the sake of it. And this is for heavy users, so users who have a lot of data, and this is for light users, right? So this is what you will get for the heavy users. This is what you get if you don't use the features in the regression, right? So for heavy users, you can see that even if you use the features, it gives you very different factor estimates than the zero mean or matrix factorization approach. That's because different users have different degrees of heaviness. Someone have rated 10 million, someone have rated hundreds of million. So the estimates are expected to be different. But this is the main thing, right? For light users who have not given you any rating, the new model pretty much is very similar to what you will get from a regression model, right? However, for heavy user, but if you look at the usual matrix factorization, there is a big blob around zero, right? So this is the key thing, right? You have a model which can gracefully fall back to the cold start model if you have light users, but then also do what matrix factorization does if you have heavy users. Right? And for users in between, it kind of does something reasonable. Okay? That's the main idea. Okay, so I probably would not go into too much detail, but how do you fit these models is important. I mean, this is a very high dimensional model, so you need to know how you're going to fit this model, right? So these are your data, this is the latent variables, these are the hyperparameters, and then the model is what is the generating mechanism of y given the latent variables and hyperparameters, and how are the latent variables generated given this, and you want to output the mode of this distribution, right? And the way it is done is you run an EM algorithm, you get an estimate of the hyperparameters, and then you use a plugin estimate, right? So usual stuff. In this case, these are the latent parameters. All the alphas and all the betas, all the u's and all the v's are latent parameters. The g's and the d's and the variance component, these are your hyperparameters. And then you do the usual EM algorithm, right? And you're done, right? Now the only thing is the E step in this case is not available in closed form. If you look at the E step, it's not available in closed form. So what we do is we compute a Monte Carlo expectation in the E step, right? So you do the Monte Carlo expectation in the E step, and then based on the Monte Carlo expectation in the E step, we do the M step, and that's how that works. If you use other methods like coordinate descent and iterated conditional modes, it is not doing the E step properly, right? So in the E step, you need to get the current mode of your estimate, and you also need to know the variance of your estimates, and you have to combine both of them to get a good estimate in the M step. The plugin methods ignore the variability in your estimate, and that's why they don't get the right estimates for hyperparameters, and that's why the performance suffers. So you either overshrink the factors or you undershrink the factors, right? So what the EM algorithm does is it kind of gives you a better shrinkage, if you will, by using the Monte Carlo sampling. Right? Again, more technical details than anything else. You can go through it and see what's going on. Right? Now, this slide, the only reason I wanted to bring up this slide is for this equation. This one. So I want you to show how this model is estimating the user factors. Right? You can see the user factors are given by a linear combination of what you will get out of a regression and out of ratings. Okay? This is the main thing I wanted to emphasize, right? So this is what happens in collaborative filtering, right? All your estimates are based on the ratings, and this is what happens in the cold start or regression approach. All your estimates are based on features. This approach gives you a linear combination of this and this. And the weights are also adapted, right? It depends on the number of ratings you have, right? That's the variance component. It also depends on what movies you have rated. If you have rated movies that are very polarizing, for instance, if you have rated movies that everybody hated or everybody loved, you don't get a lot of information about that. If you start rating a movie that was very polarizing, then that's way more informative than just. So the number of movies rated is not good enough. It also depends on what you have rated. More polarizing movies means I get more information about your ratings, and I can actually do a much better job from your ratings. Okay? That's what this equation is talking about, right? So, the value of the movie factors depend on how polarizing the movie is. So there's a lot of variability in how users rate that movie, and then the magnitude of V of J will be much larger. Right? And so your factor or your affinity will depend on how your rating is going down. Right? So anyway, I don't think this is very important. These are some results which we get by using the feature-based model, the new model, and the usual matrix factorization. So as you can see, if you use the usual matrix factorization, your performance is a little worse because you miss the cold start. So if you use both cold start and warm start, it gets better. Right? Similar kind of results on the movie lens data. And again, here we didn't just compare to the usual matrix factorization, we also compared it with other methods, other hybrid approaches, and the probabilistic methods seems to be doing much better than other methods. Probably because the probabilistic assumptions here are better. If you didn't do a good job of modeling your data, then of course it will not work. Right? Again, we ran experiments on the Yahoo front page data, and again, you see the same kind of behavior. Again, the new method is better because there are a lot of posts start in Yahoo front page, as you can imagine. A lot of users visiting only 2 or 3 times in a month, so it matters a lot, and the ROC curves kind of reflect that. The green curve is the ROC curve for the usual matrix factorization, the red one is for the new method. Right. There are many other related approaches to this, and here are a list of papers. You can read about it if you are interested in this area. I will not go into the details of these papers, but this is more for your reference than anything else. Okay, so this was more about combining cold start and warm start within the matrix factorization framework, which I believe you all are very familiar with. It's a model that has become very popular in recent times, and so the advantage is you can use the existing softwares you have and add a few components to that, and it will all start working very well. You don't have to create a new model out of it. Now I'm going to show you another factorization approach. This is more on the simplex. Okay, so how many of you have heard about LDA? Okay, so everybody knows about LDA, right? So LDA is a very good clustering model for clustering discrete data, like documents. Right? If you have documents and a bunch of words, how do you do something which is equivalent to k-means, for instance? Right? So LDA is a very good model to do that, as you've all seen. Now, what I'm going to talk about here is what is called factorized LDA. So, if you are in a recommender setting and you have documents to recommend, let's say, right? Suppose I want to recommend documents to different users. What is a naive approach? You will take the documents, you run an LDA, right? And that LDA is going to give you topical representation for each document. And then you can use them as features in your machine learning model. Right? That's one way of doing it. Now, what if I change the problem a little bit? What if I tell you, hey, why should you do an unsupervised LDA to predict your rate? Right? Can I come up with LDA topics that is learned in a supervised fashion? So if I have a document and if I know ratings given by users to that document, maybe those ratings provide you additional metadata to come up with better topical distribution. Can I actually do that? Right? That's really the main idea here. Don't just cluster the document based on the semantic knowledge you have. Also use the rating given by users with additional signals to even change the LDA topics you get out. Okay? So and again, the idea is not very, it's pretty straightforward once you do it, but it works in practice, right? So just to set notations, SIK are the user factors, just as we had UIs in the previous. I'm calling it SIK because now we have, the item factors will be on the simplex, right? So just to make sure that we are talking about the simplex problem, I'm calling it SIK. But this is very similar to the UIs I had in the previous one, right? So this is user's affinity to topic K, right? So this is the LDA topic vector you are going to get for document J in the kth topic, right? That's what you do in LDA, right? You take a document, you take a word, You generate the topic for that particular word. You keep doing that for every single word in a document, and you can average out these topical representation, and you get an average document multinomial probability in topic 1, topic 2, topic 3, and so on. Okay? So what this model is doing is it's saying, well, how the user I rates an item J depends on the user's affinity to that particular topic, which is still not learned yet, it's just representation. Okay? Okay? So, if you have an old item, then these topics are already learned from your model. If you have a new item, then you can predict these topics as the document comes online. As I was telling you, the trick here is how do I learn the topical distribution of documents by using both the semantics as well as the ranges. Right? That's really the crux of the problem. Right? And again, this is just going through the LDA topic. So since all of you know here what LDA is, I'm just going to pretty much use it to set notation in case you are using a different notation. Right? So for each topic K, you draw a word distribution, right? So that's for topic 1. This is the topic by, this is the word by topic matrix, which you're probably using on your work. Yeah. Topic 1, these are the words. This is the distribution of words for topic 1, distribution of words for topic K, and so on and so forth. Right. For each item I, for each item J, you draw a topic distribution. Item is a document, right? You draw something from a topic distribution vector, right? And then you sample the whole word topic for the topic from that vector, right? And that's how you generate the word, right? So this is the generating mechanism in LDA. This is how you generate documents. Right? So just a quick recap, right? And then you can. That's one. Okay. This is the usual LDA. Okay. So you draw the word topic, right? And then you generate the words by using the word topic distribution. This is how you generate the whole document, right? And again, these are observed. These are all latent, right? The Z's are all latent. These are unknown parameters. These are unknown parameters. This is what is observed, right? This is your data in LDA. The words you observe in document is your data. Everything else is something that gets estimated from the data. Okay. And again, the usual way of estimating the parameters is by using the EM and give sampling. And whenever you have a new item, you kind of infer about the topic by using the prior parameters that you've learned in the training phase. Okay, so this is the main thing here, right? So the main thing here is you still assume that every document has a topic representation, right? Given by the LDA, right? But these topics also show up in the response equation, right? So if you're doing an LDA, this is where you stop, right? This is how you train the whole model. But now, the per document topics which you have in LDA also are binded to the response vector in this equation. So the LDA topic assignment now will change because it is supervised both by using the words as well as the response. And I'll show you in a minute. Okay, let's forget about these equations. These are all fitting methods, but this is how it changes, right? So if you're doing the LDA, this is the fundamental equation, right? The probability of a word in the NF document getting assigned to topic K, it is given by this particular equation, right? And that's how you do your sampling, right, in LDA. Now what this model does is, because that Z's appear in the response equation as well, it tilts this equation by adding this particular. Right? So it also says, well, I want to assign the topic to topic K, not just based on the semantic information, but also I want to make sure that I assign it in a way so that it is going to increase my probability of observing what I observed for that particular topic. Right? So if you are running an LDA sampler today, everything else remains exactly the same. The only thing you have to do is just go into your code and just change this. And then it will all work. And this is very natural too, right? kind of, it's not a geometric mean, but it's kind of like that. Right? It depends on semantic, it also depends on what topic is going to increase the probability of seeing the rating of C. And then just do that. Right? So given, I don't have a lot of time yet, but what we did was we applied this method to what we call, there was a product called Yahoo Buzz. I don't know how many people here use Yahoo, but Yahoo had something called Yahoo Buzz. And the goal of that page was to show you buzzing news going on, right? And so we applied this algorithm to Yahoo Buzz because every article had a rich semantic representation. And we compared it with the matrix factorization kind of model which I was telling you earlier, and this method works extremely well there. In many other applications like movies, where we didn't have a lot of semantic information, this method was equivalent or at par with the previous method. However, this method requires more computation. Right? But given the recent advances in LDA topic modeling, especially by Alex is one of the leading researchers in this area, he's invented a lot of ways to speed up the sampling for LDA. This could actually become a more mainstream method in recommended problem than the usual matrix factorization. Because if you don't have rich semantic information, you don't lose anything compared to the previous methods. If you have a lot of rich semantic information, this can actually give you the LDA topics for free. It also not only improves the accuracy, it also gives you more interpretable topics. So now, if you are recommending something to a user, there is an opportunity for you to maybe explain to the user why you are recommending this. If you have user latent factors, then you have topic latent factors, and if your affinity to the second topic is very high, and if that topic is about the CIA interrogation, then you can tell the user, hey, look, I'm recommending you this article because you are interested in this kind of topics. If you're using something like matrix factorization, there is nothing you can tell the user, right? The machine thinks you are something, blah, 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 in some Euclidean space. You can't give that explanation. That's not understandable. But this can give you explanation, which and it's an open question today. People don't know whether providing explanations for recommendations improves things or not. In general, it is assumed so, but what has happened in the literature is models that can be explained to users tend to be rather simple. You cannot make it very complex. And so you lose a lot of predictive accuracy in the process to provide an explanation. So what we need is a model where we don't lose predictive accuracy but still could explain something to the user on why they are getting what they're getting. That I think should not work. And this could potentially grow into one of it this kind. I mean, I've not done that, but there is an opportunity to think along those lines and make it something where you don't lose predictive accuracy and yet you can provide an explanation of why you're recommending something. Right? So I'm going to show you some examples, for instance. Right? So these are some of the topics that came up, right? So this is more about CIA interrogation that was going on at that time, swine flu. Now, if you're a user and I say, okay, your latent dimension here is the highest compared to this, here, right? So you have a very high concentration here and here, and that's why I'm recommending you this article. It might make more sense to the user. The user is going to gain more trust in the system. It is all about user trust. At the end of the day, if you trust the system, you will use it a lot more. Right? And one way to gain trust is not being lackluster about it, just telling the user why you are recommending. But again, a lot of work needs to be done here. What happens if you give the wrong explanation? That might actually hurt you more than help you, right? So these are the kind of issues one has to think through. But I think the main reason I wanted to talk about this method was because of this aspect, not because it's a new machine learning method. There are many new machine learning methods. It is more about can we make the recommendation more explainable to the users. And this is just the starting point. I think I'll encourage you to think about this problem because it could be huge. When you put these things in the UI, it can really help. We have done some experiments, simple experiments at LinkedIn where we add an explanation versus not add an explanation for some simple recommendation. Adding an explanation helps a lot. It does boost the result quite a bit.
The topics, how often do you resample or very good?
So this is something which is not running in production. The previous model I showed you is running in production. So I don't have any production experience with this. This was more an offline analysis that we did. And just as in all research areas, you take a bunch of data set and you run it once and you get it done. So just to be honest, I'm not running this in production at all. This is just an idea, it seems true. I can tell you what we did in the previous one, how often and how. So in the previous one, what we did was we used to estimate the user factors once a day, and the item factors are something which we used to update every 10 minutes. Because user factors once a day is not so bad. You don't have to update user factors every 10 minutes. There are so few users who come that often. Like I can't even recall how many users. Very small number of users came to the Yahoo website 5 times in 10 minutes. I mean, many of them turn out to be bots. So you don't have to update the user factors that often. You can wait for it. That reduces computation. Like everything has a cost, right? And I'm not saying you can't do it from an engineering perspective, but whenever you do something like that, there's a cost. There's a serving cost, right? There has to be engineers who will maintain the system. So why do something like that when you don't get a lot of bang out of the cost? That's the reason why we did it like that. Even though we had the capability of it. Okay. So just to summarize this section, you're going to hear a lot about offline modeling in the other tutorial. Regularizing the factors through features is an effective technology to combine both cold start and warm start by using our good old matrix factorization, right? And so you're all familiar with that, you're so used to it, you've seen it work very well. This is just an additional wrinkle, if you will, in that same framework. So, and it is effective, right? So I think I would encourage you to think about it this way, because all your software and code can be reused without too much modifications. That's the main reason. And the fitting methods are scalable. Yeah, it involves some GIF samplers and other things in the E step. But given the recent advances that have been made in this area, you can scale it up. We have also scaled it up when we implemented it. We scaled it up on Hadoop. This was 2 years ago, so a lot has happened in the last 2 years in terms of computing infra. But 2 years ago, we were able to scale it up even on Hadoop by using some approximation, right? So we'll we'll divide the users randomly into different subsets. We'll run different models, and then we will average the results. And that's how we did it 2 years ago, and that was an effective strategy to scale these models. Okay, so this is all I would cover in the offline component, and now I think we can move more to the near online component. So this was these are computations which you will do once a week or once a day. These are the more stable components. Okay. So first of all,
can you just give us a minute to change the memory card?
Just 1 second. And we're live again. By the way, the camera doesn't see you there.
Oh, okay. Good now?
Sort of, kind of. I think if you stand in the middle,
Maybe I'll
see
see
you better.
This is better.
Yeah.
Okay, so why do you need online components, right? And, so the number one reason is cold start, right? New users and new items keep coming to the system continuously on most web applications. Right? And how do you obtain data for new items and new users, right? So one way is to do explore exploit. That's an online computation which you have to do. Once you get data available, how do you adapt your estimate very quickly to provide better estimates for these new users and new items that come to the system? Okay? So that's what I'm going to talk about, right? How do you collect data so that you can deal with the cold start problems through explore exploit methodologies? Once you collect this data, how do you update your models to kind of reflect the information very quickly? right, and improve the recommendations. Okay. Then there is also concept drift, right? So most of the web applications are highly non-stationary and things change over time. So you have to constantly be adapting. Even if you don't have items that are too ephemeral, you still want to adapt your system because things could be non-stationary, right? Users' behavior might change. A big event in the world can completely change users' preference for items. And your old models may not be germane anymore. And if you take a long time, then you again may not engage the users as much as you could if you continuously adapt your system. Okay. Okay. So this is how I'm going to go about it, right? So I'm going to talk about some time series model, visualization, explore. Let's see how far we go. Okay. So in order to understand, let's go back to our whole example of doing most popular recommendation. Again, this is meant to be a baseline. It is meant more. I'm using it more for expository reasons than anything else, but it helps us understand because the math is simple. You can see what's going on rather than going more complex right away, right? Okay, so no personalization, and you know, I'm going to talk about all these three components. And by the way, this model, although it looks very simple, sometimes it's pretty hard to beat. Like even if you try to personalize, sometimes this is very hard to beat in terms of the metrics. So it's good to have this anyways in your system, even if you are going for a more complex model, because the baseline is strong. Okay. And again, it is easy to extend this, right? So you can still do light personalization if you have implemented this. How? You can just create some coarse user segments, and then you run most popular within each of the segments. So light personalization is even possible with this method. Okay. Right, so this is the usual recommendation problem. I talked about this, and you know, these are the challenges. We know about that. The same old example, right? And the thing I want to focus on is articles. They have short lifetimes. There are temporal effects, and there are often breaking news stories that come up, and so you have to react to that very fast. Right? This is all. I already talked about these things for this application. So. Right, so the first problem is how do you track CTR over time? Right? You've already seen that CTR kind of having a strong non-stationary pattern, right? So what kind of time series models you can build, right? And so one model is the Kelvin filter model. There are some other options. So the simplest option is, in order to predict the next time interval, you look at the clicks and views in the previous time interval per article and just estimate the CTR based on the previous time interval. Now this is going to have very high variance, as we all know, because for many articles, the number of times you showed that article in the last 10 minutes or 5 minutes will be extremely small, right? So you get very unstable numbers. The other is just count the total number of clicks that have been obtained by that item since it was born, and the total number of times it has been shown in the diagram. Now that is stable, but it reacts to changes slowly, right? If there is a big diurnal pattern, it will take a long time to adapt. The other thing is moving window, right? You look at a small window. Okay, let me look at the last 1 hour and then estimate CTR based on the data I have about an item for the last 1 hour. That's the moving average approach, and that is reasonable. But it is not very easy to incorporate prior information you may have about the article in a very natural way when you're doing moving average. You can do it. I'm not saying you can't do it, but it's not very natural, right? Right? So one way is to just use a generative model, right? I mean, you know, if you have prior information, you can easily incorporate that. It does what you get out of moving average. It kind of gives more weight to recent data and less weight to past data, except that the decay function is slightly different, but it still does the same thing. So you kind of get the best of both worlds. You can incorporate prior information, and you can also do what you want to do, which is weigh the recent data more than the past data. Right? So that is one way of doing it. Right? So this is for a given item. The number of clicks you get is, let's say it's a person or binomial, and then you have a state equation, and then these are this is the model parameter you have about. This is the prior distribution you have for the item at the first time interval. It has some mean and some variance, right? And the eta determines how much weight you give to more recent data in the past data. Right? So if the data is very large, then you give more weight to more recent data. If data is small, then you give less weight to kind of uniformly weight data, historical data. Right? And you can easily solve this recursively by using usual procedures. This is what the graphical representation looks like. I'm not going to go through the equation, but you can solve this from first principles by using the usual Kalman filter and Bayesian machinery, right? And at the end of the day, this is your estimated CTR for the next time interval. It's a gamma distribution with this variance, and the mean is exactly the same as the posterior mean you had in the previous time interval, and the variance is the posterior variance you had in the previous time interval plus some dilation. Okay? If you don't have any dilation, then the posterior variance will keep tightening up, and you will not give more weight to recent data. So you have to dilate the variance a little bit, and the dilation will depend on this eta parameter. It will depend on whether the article has high CTR or not. So if you have articles with very high CTR, they will adapt more quickly than articles that have lower CTR. And of course, the parameters. So this is an example. Like, so this is the model that was fitted by using this previous data. So one thing I want you to see here is articles that have higher CTR are more adaptive than articles that have lower CTR. And that's because of the multiplicative state equation. When you have a multiplicative state equation, the window that is used to weight recent data changes. Right? Articles that tend to have more clicks will use a smaller time window. Articles that have fewer clicks will use a larger time window. That's what multiplicative state equation does for you. If you have an additive state equation, then that will not happen. Everybody will have the same kind of weight. But for these kind of applications, this makes more sense. Because the more clicks you have, the more data you have, and you can be more adaptive without being killed by the variance of your estimates. Right? So that's the main idea. Okay. You can also use all the historical data about items you have to come up with better estimates of prior means and prior variance. Okay. So what you can do is you can say, okay, well, in the past I have shown 1 million items on the Yahoo front page. Let me take that data and figure out what kind of starting point is going to give me the best explanation of the curves I have seen. Right? You can do that. That's what this is doing. Without going through the details, that's what it is doing. It's taking all the historical items, looking at all the time series trajectories, and figuring out what prior estimate is going to explain those trajectories in the best possible way. You can do that. Even without requiring any metadata on the item, you can get a good prior mean and prior variance. So that's why I meant by intelligent initialization. Just using the historical item data, you can come up with a better way to start your estimates for new items that are going to be seen in the system. So this is not absolute cold start. Absolute cold start is some product manager launched a product today and you have not seen this at all in your life before. Right? This is the Yahoo front page has been running since 1995, so you have a lot of data. Right? So it's not absolute cold start. Okay. Okay, so now how do you do explore exploit, right? So before I go into the solution, let me first describe the problem, right? And then we will do as many solutions as we can in the talk, but I want to make sure you know exactly what the problem is, right? Mathematically, so that you can think about it, right? So you are here at any given point in time. You are in interval t. Let's say each interval is of 10 minutes. So here you have k different items, and you want to decide what fraction of page views should go to item 1, what fraction of page views should go to item 2, and so on and so forth in the next item. Okay? So this is the design you want, right? You have k items, let's say you have 100 items. You want to decide in the next time interval, should I give 2% of page views to item 1, or should I give 3% to item 1? How much, right? And if these x's are your design parameters. Right? So trying to figure out what is the best fractional allocation scheme you can come up with in the next time interval to improve the overall clicks of the system in the long term. And this is again ignoring personalization and all that stuff, right? I've already told you that. Right? So this is the design problem. Okay? And you have all the data you have seen so far to kind of make this decision. What's the best you can do? So if you are myopic, you will say, well, let me look at the empirical CTR of all articles. The one that has the highest CTR gets 100% of the page views in the next interval. Everything else gets 0. That's a myopic solution, greedy solution. You can call it the greedy solution. It does not look forward. It just looks at the instantaneous CTR and makes a decision based on that. And in the next time interval, that article that has the highest empirical CTR gets 100% of the page views. And then you again recompute your empirical CTRs and do the same thing for the next time interval, right? So that's a design. It's not the most efficient because it's not going to give you the best solution, as you will see. Okay. So is the problem definition clear? Right, okay. Yeah, so in order to come up with a solution, you should not look at what has just transpired. You should also try to look ahead in the future. If I take a particular action in the next time interval, what impact is it going to have in the future? Right, that's the key here. That's why the computation becomes difficult. If I show you, if I dedicate 2% of the page views to article 1, article 2, article 3, and then the rest to article 5, I'm going to get some data, hypothetical data out of that. I'm going to revise my estimate out of that hypothetical data. What is that going to do for the next time? That's the computation you have to do. And then I'm going to get another data out of that, and that's going to impact my third time interval. So smells like dynamic programming, right? And that's what it is at the end of the day. Okay, this is the good old picture for two items, right? Right, and as I was saying, if you have to just make a single decision, the myopic is the best thing, right? If the Yahoo front page is going to shut down after 5 minutes, that's the best you can do. Just take the best empirical CTR article, show it, done. Right? That's not the case. You have to assume that your front page is going to be running for the next month. What is the best thing you can do? Kind of make that monthly clicks as much as possible, right? And that's why you have to look at the potential of an article to do well. Right? So this article, although it has a lower mean CTR, it has the potential of being better than this particular article. And then you can write down this potential as some tail expectation. Right? This is the tail expectation. Okay. And as I was telling you, it is related to the multi-horn bandit, right? So every slot machine is like an article, and just as in the multi-horn bandit literature, you have unknown payoffs, you have unknown CTRs, and there's a lot of literature here. In the bandit literature, you have to pull the arm sequentially. You pull an arm, you see the feedback, you make the next optimal decision, right? So it's the same kind of problem. Right? And there are two ways. One popular way of measuring the quality of a bandit policy is what is called regret. So what is a regret? If I knew the true CTR, I know what I can get. Now if I run a scheme, how much do I lose relative to that? Right? That's the regret of the scheme. Right? So it's often used as a way to measure the quality of a bandit scheme. Okay. Right? And so there are two different ways of solving the bandit problem in the literature. One is a Bayesian approach, where you seek to find the Bayes optimal solution by writing down an MDP. Of course, it depends on the assumptions you make on the distribution, right? So if you're taking the Bayesian approach, the quality of the solution really depends on what kind of modeling you are doing, right? If your models are good, then you get very good answers. If the models are not very good, it will not be very good. And then there is more like a minimax kind of approach, which tends to find scheme that can bound the regret you have incurred by some factor, like logarithmic factor. And these are more robust to modeling assumptions, but you can often do a much better job of doing the Bayesian scheme if you do the modeling right. You will cut down the exploration by part. But again, you have to spend a lot of time doing the modeling, right? So that's the trade-off. If you're willing to do a good job of modeling, you are better off with the Bayesian schemes. If you don't have the time to do modeling and you just want to get something out of the door very quickly, then these schemes are not bad. It's at least giving you some sensible schemes to do exploration. So both of them are useful in practice, especially when you're working in an industrial setting. Sometimes you won't have the time to do modeling. You have to roll out something in 3 days, and then, okay, well, is there something I can do quickly? I don't want to do any machine learning or any probabilistic modeling because I don't have the time. Well, yeah, UCB is your friend. Just go and implement it, and you'll be okay. So it's good to know both. And again, having this as a baseline is also good, right? Because it kind of keeps you honest as far as your model quality is concerned. Let me skip some details. Skip section here. Okay. Oops. So sorry, something happened. I did not want to skip there. Oh. Skip to the wrong place. Sorry. Okay, sorry about that. Yeah, so I'm not going to go in detail with this slide, but this is how you can write the model as an MDP, right? So if you're interested in the Bayesian approach, then you can write it as an MDP, right? And so I'm going to go through just this last thing here. So this is the policy or the explore-exploit scheme you want to construct. And so this is saying, okay, this is the value of my policy after t time intervals, right? I start with the initial state, theta 0. The state could be the number of clicks and number of views you have for each article, right? So, and this is the value. So this, what will be this value? Well, if I start with this state, and if I use this explore-exploit policy, I'm going to move to this state after one time interval, right? Right. So if I start from this, I move to this, and then the value which I'm going to incur after this is going to be the value which I incur after t minus 1 if I had started with this, right? So the usual dynamic programming, you can write this expectation by using the transition probability of this to this and so on and so forth. And then the goal is to really come up with an optimal solution to this MDP, which is not very easy, as we all know, right? MDPs are hard to solve computationally, right? And I think the main breakthrough that happened in this area was by Gittins. So what he said was, well, let's change the reward function to something like this, right? So instead of saying how much reward I'm going to get in t time intervals, let's say, well, let's write down the total reward as something which is more like a geometric average of rewards from time 0 to ad infinitum, right? Instead of looking at reward in a finite time interval, do an exponential weighted moving average of the rewards by using this parameter. And then he was able to prove that the optimal policy which you will get can be solved by decoupling the problem, right? So instead of solving a joint optimization problem from k independent for k arms, you can actually solve it by solving k independent one-dimensional problems. So for every arm, you compute what is called the Gittins index, priority of that arm, and then you choose the arm that has the highest priority. Right? So every arm runs a one-dimensional optimization problem. It gives you the priority for that arm, and then you choose the arm that has the highest priority. That is the, so it showed that solution is an optimal solution to this MDP, right? Which was a breakthrough result. Right? So the main takeaway from that is you can solve the k-dimensional problem by solving k one-dimensional problem. That's really the main thing, right? If you keep adding more arms, doesn't matter. You just solve a few more one-dimensional problems. Okay, and the high-level idea is the Gittins index is something that measures the potential of the arm being good. Right? So, for instance, if I have to explain it very naively, this is not exactly Gittins index, but if I have a CTR distribution of an article, instead of scoring articles by using the mean, score it by using the 95th percentile. Right? That's an optimistic estimate of the CTR. And so, what Gittins policy intuitively is saying is score the article based on their potential of being good rather than using the mean. And that's essentially what it is. Now, the kind of computations you have to do to estimate the potential is different than what I just described, but just to give you an idea, think about it that way, right? Use the 95th percentile instead of the mean to measure the quality of an article, and just rank based on that, and you'll get something similar to what Gittins index is talking about. Okay, so I think I'm not going through this. Yeah, so there are ways of computing the Gittins index, and there are a lot of papers talking about that. I would especially recommend this paper by Lally et al., where he derived how to compute Gittins index for exponential family distribution, right? So binomial, Poisson, all of that can be computed by using this paper. And then there is this minimax approach, right? So the one important word here is what is called the upper confidence bound policy, and the idea is similar to what I was just describing, right? So instead of ranking the arms just by using the empirical CTR, add some uncertainty estimate also. Right? So this gives you an estimate of how potential, what is the potential of that arm being good, right? And you do that and have a speed. How you measure this potential determines how much exploration you do. So you have to do it carefully, but the idea is the same. So as you can see, there are no modeling assumption here in the UCB1 scheme, right? It's derived in a very non-parametric fashion. Right? So n is the number of page views you already have, ni is the number of page views you have for RMI, and then you just rank them based on that. So I'm not going through that again. So this is the observed payoff. This is the payoff representing uncertainty. And there are, you can show that this scheme has logarithmic bounds, but unfortunately the constants in these bounds matter in practice. So if you write down the theorem, the constants don't seem to matter too much, but in practice the constants do matter. Reducing that constant, tightening it up is actually important for getting good performance in practice. Right. There are some other schemes, heuristic schemes, that are often used in practice. Epsilon greedy, we have already talked about that. You take a small fraction and randomly explore items, and you use all that data to learn about your system. It's not bad. You may have to spend some time to tweak the epsilon, but it's not a bad starting point in an application. Okay, so if you have nothing to start with, I would just recommend starting with epsilon greedy. Then there is something called softmax. So the beauty of softmax is you don't need to get any variance estimates. Right? If you have the empirical CPR, you modulate the probability of picking an RMI by using a temperature parameter. Right? So if the temperature becomes infinite, then you are doing uniform exploration. If the temperature becomes 0, then you are kind of picking the arm with the best CPR. And so if you tweak this temperature carefully, I've seen in real life it works to do that. But you have to tweak it. It is very sensitive to the choice of that parameter in empirical applications. And then something that has really gained a lot of acceptance recently is Thompson sampling. So if you take a probabilistic framework and you can get the posterior distribution of your CTR estimates, what Thompson sampling is telling you is you just draw a sample from your posterior distribution and use that as your score. So if I have a CTR distribution, beta binomial CTR distribution for article 1, article 2, instead of ranking the articles by their mean estimate, you draw a sample from these posteriors. For every visit, draw a sample from the posterior and use that as a score to rank all. So this is inherently introducing some jitter into your estimates, and the jitter is coming through the distribution itself. Right? And there have been papers recently that have also shown that this is logarithmically bounded, and many people have used it in practice, including myself, and it is actually pretty good, right? Actually, it is simple, right? Because now the complexity of explore exploit is all gone, right? If you spend the time to build a good model, a probabilistic model, and the probabilistic model can spit out both the mean and variance estimates, you are in business. You have solved both the problems at the same time. But you have to spend a lot more effort in coming up with good probabilistic models, because now the probabilistic models cannot just give you the right estimate of the mode. They have to give you the right estimate of the posterior, and that's a much harder problem. And so you have to be careful of that. Okay, so that was all about the multi-arm bandit problem. But if you're in the recommender setting, there are some assumptions that are violated compared to the bandit literature. One is you have a dynamic set of arms. Many of the multi-arm bandit literature assumes you have a fixed set of arms, except for Whittle's paper. Whittle kind of assumes that he calls it the restless bandits. But that's other than that, most of the papers assume that the set of arms are static. CTRs are assumed to be stationary. The payoff probabilities don't change in multi-arm bandit, but it could change. And finally, I think this is very important. A multi-arm bandit assumes that the feedback is available without any delay. You assume instantaneous feedback. In web, that doesn't happen, right? Because once a user interacts with the article, I showed you that picture, the architecture diagram, right? The front end has to transmit the event. It takes time before it comes to the back end, and the data is available for processing, right? So realistically, it takes 5 to 10 minutes before you can actually react to So you have to come up with batch serving schemes, which is different from what multi-unbounded literature talks about. Okay. So as a practical consideration, I think using Thompson sampling, softmax, these are epsilon greedy. They are very good practical solutions. And what you use would depend on how much work you have done. Right? So you've not done any work in terms of modeling. By modeling, I mean both the mean and variance, not just the mean. Then it's good to go with epsilon greedy first. And then once you collect some randomized data from your system so that you can do offline evaluation, you start doing softmax. The offline data will help you tweak the softmax parameters. And then once you have done softmax, hopefully by that time you have built a probabilistic model, then you can start doing Thompson sampling. So I will go with that. Okay. Okay. Now, I think for the simple, most popular problem, it turns out you can compute the Bayes optimal solution. So I was hoping to show you that. We have 10 minutes. Maybe I'll just show you that. I'm not recommending this be used in system at all. You can use it. We have used it on Yahoo front page and it actually works pretty well. But you don't necessarily have to use it. All I'm trying to show you here is how you do this computation from the first principles. So if you are doing more research in this area, you can latch on to the first principles we have here and extend it to the other problems, if you wish. Right? All the other methods I talked about, Thompson sampling, softmax, UCD, these are all heuristics. Right? They're not Bayes optimal in any sense at all. Right? But computing Bayes optimal for all the personalized recommendations is a hard problem. So I'm going to show you how we do it for the most popular recommendation. We have not solved it for personalized recommendations, and hopefully you can do more research and use the ideas to generalize it to other problems as well. Right? So that's the thing. So same view now. At T0 you have N0 views, and at T1 you will have N1 views. Right? So N1 page views now and N0 here. Right? Let's try to do it for two articles. Right? So item P is the one that has uncertain CTR. Item Q has been shown for a long time, and the CTR of that is exactly no uncertainty. Right? So the CTR of item 2 is Q0 at the moment, and Q1 for the interval where you want to make a recommendation. Okay? So this is what the picture looks like. That's the good old picture. Right? And P0, Q0 is for the current time interval. Now, P1, Q1 is the hypothetical CTR which I'm going to get in the next time interval. Yeah? And again, that will depend on how much page views you allocate to these things. Right? That is important. Right? So that's the problem. What fraction of the current page views where you have to make a decision needs to be allocated to item P? That's the design parameter you need to determine for this two-item problem. Right? What is the value of X? What is the optimum value of X? If you are just looking ahead 2 time intervals, right? What I do now, I want to see what I do now would impact the current interval and the next one. Only 2. In general, we want to do K, but let's say we do only 2. What is the solution to this problem? And so in order to determine X, we have to estimate what will happen in the future. Once I give X page views to this item now, what repercussions will it have for the next time interval, and then do the calculation. So that's why we need to do some more computation. So suppose I show a certain number of page views, right? Let's say I show X% of N0 page views to item P, right? That's going to give me C hypothetical clicks. If I show it 1,000,000 times, I'm going to get a certain number of clicks. If I show it 100 times, I'm going to get a certain number of clicks. Right? So that C is the random variable. Right? After showing this article, the random variable. Once I observe the hypothetical number of clicks which I'm going to get by showing this article, I can update the posterior distribution of that article, right? Based on hypothetical clicks. Right? So both if I know X and if I know what number of clicks I'm going to get, I can update the posterior distribution from P0 to P1, right? And then, if my game ends at the next time interval, I'm going to allocate all the page views to item P in the subsequent time interval if that posterior mean is bigger than Q1. Q1 is the CTR of the uncertain article in the next time interval. If it is less than Q1, then I'm not going to give any page views to that. Okay? Because if the game is going to end in the next time interval, in the next time interval, you've got to be myopic. Give all the pages to the article which is the best, and nothing to the other one, right? So that's what happens. Okay? Right? And this P1, the posterior mean which you're going to get for the uncertain article, is a function of x, the number of pages you give to that article, and also the hypothetical clicks you're going to get in the next time. Right? It's a function of both x and c. Okay? And so, if you write down this equation by looking at 2 time intervals, this is the expected number of clicks you're going to get for the system, right? So, x is the number of number of pages you gave to the uncertain article. So, x times p0 times this is the number of pages you have, and this is the uncertain article, and this is the important thing, right? So, if this guy is bigger than this, then all the page views go to the certain article in the subsequent time view. If this guy is less than this, then all the page view goes to a certain article in the subsequent time view. Right? So if you compute the expectation of this with respect to the marginal distribution of the hypothetical number of clicks, then we get doing a 2-stage calculation. And if you solve it. So this is the number of clicks you would have obtained if you had shown only the certain articles in both the time intervals, right? Now rearrange these terms. So this is the amount. This is the gain in clicks you get by doing this explore exploit, right? And your goal is to find the value of x that is going to maximize the gain, additional gain you get over following the myopic scheme, right? So that's the well-defined optimization problem. And you can solve it. I'm not going to go through the solution. You can write down the gain function and you can solve it, and you can get an optimizer. Right? So this is how the scheme. You can actually do this computation from the first principle and get an optimizer. You don't have to. And the reason you can't just appeal to something in the literature and apply it as it is because the assumptions are valid. That's why you have to start from this. Okay? And okay, so I'm not going to go through the quiz and all. Then you can generalize this to k items as well by using some Lagrange relaxation technique. I think most of the material is borrowed from Whittle's paper in 1980s. He also did some similar computation for restless packets. Right? And from 2 intervals, you can generalize it to multiple intervals as well. You can generalize it to non-stationary CTRs as well. It doesn't matter what your distribution is. As long as you have a probabilistic model that can give you the posterior distribution, you can just plug it in this way. Okay? When we ran some simulation with this scheme and compared it with the other scheme, then obviously it is better because otherwise I won't be discussing this. Okay, but that's not the point I'm trying to make. The point I'm trying to make here is what we have seen in the simulation is if your data is modeled very well by the distribution, then the Bayesian scheme is much better than using the other schemes. So that's the message I was giving you at the beginning of the section. And so, yeah, I think I don't have to explain the other things, right? So I'm just going to go through this plot, right? So this is the base 2 by 2 base general. Again, these are 2 different variations of what I was describing for 2 items. This is the UCD scheme, the usual UCD scheme, then epsilon greedy, softmax. This is the average number of articles you have in every single interval, right? So if the item pool becomes larger, the quality of the schemes becomes different, right? And this is the regret, right? As you can see, it is natural, right? If the number of articles becomes larger, then the regret is tends to because the explore exploit problem becomes more challenging. So these are the Bayesian schemes right here. And then you can see the regret is uniformly lower than all the other schemes. But that's because the data follows the distributional assumptions. If you do a simulation where you fit a completely wrong distribution, then this won't hold. If the distribution assumptions are right, then it seems like the Bayesian schemes are much better. The softmax is not that bad, and again, the curve I'm showing you here was obtained by doing a lot of tuning. So I'm showing you the best softmax variable. If you don't do tuning, then the softmax performance could be rather arbitrary. You have to be careful of how you The UCB scheme tends to do more exploration. If you use the UCB as it is, the variance estimates are rather generous because it's based on non-parametric churned up of the bounds, so it tends to overexplore. That's the problem. So, okay, so with that, I think we are out of time today, so we can continue tomorrow. Tomorrow I'm going to cover some online model upgrade scheme, and I'm going to cover multi-objective optimization with an example.
Yeah. Actually, well, I know what else happened. I was like, I've never actually kind of. Yeah, that's kind of. I mean, haven't talked yet. That was we do porcelain that like for the microwave from like and also need that. What a surprise. Yeah, I think looks like less underwater sounding than the other one. Well, I mean I will, but you know, in more than 2 hours time. So if you want to, yes, yes, moving on. Especially if you check for our slides. Well, I mean, I would have had a whole lot of pretty exams. Well, I mean, you get an ontology if you do want. I mean, yes, you can get ontology, but actually, you can do two things. You can either have an ontology, or you can have an ontology. Those are so those two things are very different, right? You can get either one of them. You could actually possibly get both at the same time,
That would be a fair amount. Some of the actually work very detailed, but yeah, it should be about. Yeah. Okay. Okay. Yeah. Okay. Tell me. I just need to keep up your lunch. Yeah, just maybe need to make sure that the speakers are well taken care of. But
Well, I don't know if it's published.
Those are all.
they're all us. Just make sure that it's very clear that they are. Okay. Oh yeah.
Really fun.
Yeah.
Ways to just
Here are 1, 2, 3 B's.
What are those?
Those the 3 walls with you.
Oh yeah, the garage door.
Well, not just no, they're a little bit faster than that, but basically for normal arms, all the things that you use them to the house. Cool.
Yeah, no, you did. I should look into that. I mean,
It's just like cheaper than anything else.
Okay.
Yeah. And you can check the status of the alarms from online.
Right. Yeah.
Yeah, I think that's a good
I mean,
idea.
I looked a lot, and it's supposed to check the status, so I find that actually we have a unit with module. I would say last time I got home and I checked the system and it was disarmed at like 3 a.m. But when I arrived, it was really late. And then I got a phone call. And it's actually recorded by voicemail, maybe I'll have the voicemail. But it was very clear that the person was barely able to make that. Who checked them all.
Wait, so this is not the same as this?
No, this is simply safe, but basically they send an alert back to the base, back to base.
Yeah.
And then somebody will actually call. And if it had been an alarm rather than just a case, it would have actually, they would have called the police. So in that sense, I mean, they're basically as safe as anybody else.
Right.
Well, how unfortunate, because then we would feed you.
Oh, by the way, I looked a little bit more in the balance stuff. No, but I did. I know. So I know it is so sad, but it's obvious why it's true, because you come up and all you know is the pairwise.
Wait a minute, why did somebody stop this? This doesn't make any sense.
Oh. It's not like it's not a window open.
I mean, they're here. No, but it says live at the same time. Why is this machine so slow? Oh, because somebody changed the screen.